So good morning, everyone. My name is Kurt Smith. I'm a software developer at Unthought, and I've been with Unthought for 4 years. My area of specialty is, I guess, Python and other languages. So Cython fits in there very well, getting Python to work with C, C++, Fortran. Those are the main languages. And I work primarily in consulting, also do training, and have developed a good amount of training material based on Cython and other things, high-performance computing with Python, other topics relating to Python and compiled languages typically. So this tutorial is something I've given a number of times now, iterate each time and add more material, improve it, that sort of thing. And so it's very familiar to me. So I'm happy to talk about Cython in depth now, certainly at the tutorial and then afterwards also. I believe it still has a lot to give people, even in this new age of JIT compilers, that sort of thing. We'll talk about Cython and how it can stay relevant towards the end here. But I'm glad you're all here, and I hope you are as excited as I am about what Cython can bring and what it can give you and what benefits it can bring to your Python code. So also by way of just getting a feel for who I'm speaking to, who here, just in way of experience, raise your hand if you have at least, let's say about a year or so of programming experience. At least a year. Excellent. Keep your hand up if you have at least 3 years, 5 years, 10 years. Okay, fantastic. So fairly experienced group, which is very good. So that helps me gauge kind of where to pitch things. So I'd like to jump right in to show you what Cython is. Actually, another last question I promise for this morning. Who here has ever worked with Cython before already? Okay, a number of you. So about half and half. So I'll try to give things for people that are perhaps more familiar with Cython, and then people who haven't seen it before, we'll make sure you're not left behind as well. So I'd like to jump right in. On the left here, we have a very simple Python function, computing the Fibonacci sequence using a for loop. We're using Python's multiple assignment and a simple for I in range n, and that sort of thing. It's very straightforward if you know Python. On the right, we have a C or C++ equivalent. And it's a little bit more verbose, but of course you can more or less squint and see that it's doing the same thing. Okay. Now, we know it's not exactly the same thing because a C or C++ integer is very different from a Python integer. Python integers are, you can basically conceptually think of them as unlimited precision, that sort of thing. But in terms of just the steps that are being carried out here, they're doing the same thing. And the nice thing about Cython is you can kind of think, it'd be nice if I could take the Python version and combine it with the C and C++ version in some way. And more or less, we're just talking about adding the type information from C and C++, adding that static type information to Python. And that's what Cython gives us in a nutshell. Down at the bottom here, we have the Cython version of this. It's almost exactly the Python version. I've highlighted in red here the additions, the things that are different. And you see we're adding an int n to the argument. We're declaring I, a, and b as integers as well. But the body of this function is identical to the Python version. So this kind of points out that Cython is mostly Python. Often you start with Python code, and you're adding in C information, hopefully a minimal amount of C typing information to make it work. And it's this hybrid language. It's this Creole language, if you will. It's able to combine programming languages in a nice way, in a fairly natural way. And without me telling you, if you've never seen this before and you just looked at this Cython code, if you already knew Python, you'd pretty much get a sense for what's going on here. Right? It's not surprising what's happening. And that's another nice thing about Cython, is you can leverage your existing Python knowledge a lot with it. It can take just regular Python code and it will compile and work. And then you can optionally add this typing information to improve its performance. So what about that performance? Well, if the Python version takes 1 unit of time, then the C or C++ version is about 2 orders of magnitude faster. And the Cython version is just about 2 orders of magnitude as well. And here there's definitely some subtleties here in terms of, the C and C++ version doesn't have to deal with Python objects anywhere. It doesn't have to convert Python integers into C integers, that sort of thing. The Cython version does. It has to take a Python integer, convert it into a C integer to do its work. So there's definitely some overhead in converting back and forth between C and Python types. So the Cython version takes a little hit from that. But overall, we're getting the same order of magnitude speed up from the Cython version. And the nice thing is that Cython also integrates closely with your existing Python workflows and Python code. So you don't have to, it's not as much effort to get it working. And of course, for the record, if we were to just go all the way and write this extension module by hand, by the way, an extension module it's a Python module that you write in C. Okay? And you compile it into a shared object file in some fashion, and then Python allows you to import that and use it. So if we were to write this simple little Fibonacci calculation all the way in C, no Cython anywhere in here, you don't have to do too much, but you do have to know a good amount of the Python C API. Its performance is only 25 times faster. So if you remember back here, our Cython version is 80 times faster. It's basically generating more or less the same code here. It's generating C code for us that creates an extension module, but you can tell already that it's generating code that has significantly better performance than the handwritten version here. And there are various tricks and things Cython is doing to get that better performance, but Cython takes great pains to make sure that the code it's generating is extremely efficient and is extremely good at converting between C and Python types effectively and efficiently. So that's Cython in a nutshell. Let's talk about it in a little bit more detail. You can think of Cython as a language in and of itself. And it's a Python-like language. You start with Python, and it allows us to improve Python's performance. For certain things, you can get 3 orders of magnitude speed up. It's not uncommon, especially for loop-heavy code, lots of iteration, that sort of thing. And it also allows us to wrap external libraries. If we have C, C++, even Fortran code, it's easy to use Cython to create nice wrappers for that code. So these are the 2 main things Cython's used for: improving Python's performance and wrapping or exposing external libraries to Python. And we'll see both of those examples today. There's a Cython command, compiler command, and its job is to generate optimized C, C++ source file from a Cython source file. So our Cython source code that we'll see here in more depth, it's kind of it's the source that Cython starts with, and then Cython generates an extension module from that Cython source file. And then that extension module is compiled into a binary extension module. Several other things that are worth pointing out about Cython: it has built-in support for NumPy, works very well with NumPy arrays. It integrates well with IPython. There are IPython commands for working with Cython. And as we'll see in the next slide here, it's foundational to the scientific Python ecosystem. And even you could say that the data science, the Python data science ecosystem. So just to give you a feel for who's using Cython, and just to emphasize that it's here and it's here to stay. It's not some side project. It's not some little thing a few people are using. It's really at the core of everything we're using, certainly at this conference. I don't know if people have heard of Sage before. There's a Sage project that has an impressive amount of functionality, often more for pure math, but it really was an original driver of Cython. The Cython project has almost 500,000 lines of Cython code. I think it has more Cython code than Python code, actually. NumPy, of course, uses Cython a little bit, and then SciPy uses it certainly a lot more. Pandas is definitely worth pointing out. Pandas uses Cython significantly for a lot of its heavy lifting code. LXML is a very popular XML library. One of the Cython core developers also develops LXML, so it uses Cython significantly for XML processing. Scikit's image, Scikit's learn, MPI for Pi, YT for sophisticated astrophysical data sets, management and visualization, that sort of thing. These are all big projects that are using Cython heavily and significantly, and they're committed to using it. Okay? And you're using Cython, almost guarantee you're using Cython every day perhaps without even knowing it, or at least using Cython-generated code. So to break things down a little bit more, the Cython workflow. We start with a Cython source file, usually with a .pyx extension. And somehow or another, the Cython compiler is called on it. It generates a C extension file or C++ extension file, usually named fib.c, something like that. This may be going on behind the scenes. You may be doing this explicitly, but somehow or another, Cython needs to take the source file, generate the C extension file from it, and then you use a standard compiler to create a extension module, a Python extension module from that sort C extension file here. And if we're wrapping, then we would also compile in the code we're wrapping as part of this extension module here. Okay. So we have kind of one compiler, the Cython compiler, which generates C code from our Cython source file, and then we have a just regular C compiler that creates our dynamic library for us. And then to emphasize the two modes that you can use Cython in, you can start with Python code, add type information to it to make Cython code out of it, and then Cython will generate the C code for us. Okay. Or we can think of it as, this is one direction, starting with Python and wanting to get to compiled code. Or we can start with compiled code, C, C++, and we want to be able to use it from Python. And then we can use Cython as the middle layer here to describe the interface of this library and have Cython generate a Python extension module that exposes that code to Python. Okay? So you can think of Cython as working in two directions. Right? Start with Python, add type information, create a compiled extension module that speeds things up for us. Or starting with compiled code, C++ code, exposing that with Cython to Python, and then getting a Python extension module that can call into that library. Yes? So the question is there another project or another? Yeah, there's several actually there are several wrapper projects that can automatically wrap code or allow you to expose code. Some are like Swig. Swig is a big one. SIP is another one. Boost Python is another one. There's several out there.
Are they same, different?
So there are lots of points you can compare them on. We'll see what Cython does, of course, in a little bit. Some of them are more automatic than others. Some of them give you more control than others. Some of them are more C++ centric, that sort of thing. I've used Swig a lot as well because it's automatic. Yeah, and so we'll see. Hopefully, I'll point out the relevant differences as we go along. Okay, so we're going to experience in a little bit here with an exercise, but just to walk you through the steps. Here we have a very simple fib.pyx source file. And here we have a simple setup fib.py. So this is our distutils script whose job is to compile our extension module for us. Okay? And Cython knows how to work with this, with distutils. And so it gives a very nice high-level interface for doing this sort of thing. And really the core thing here is a Cythonize command. And it knows how to take the file name for a Python extension module, fib.pyx, and generate the right extension stuff and basically instruct distutils how to compile this thing. So we really need essentially just these 3 lines. 2 of them are imports, and then 1 of them is a function call. And really, Cythonize is just doing all the work here for us. The rest of it is more or less just set up for us. Okay. And so we'll be seeing that in a little bit, but it's a very minimal effort on our end to have a simple distutils setup script that will compile Cython code. And we'll also see, compilation steps. This is more for reference for you when you're working on the exercises, that sort of thing. So Mac and Linux will be calling it like this: Python script name build ext. This is the command we're giving distutils. We're telling it to build an extension module. And then we're also saying put the results of that build process in this directory, so I don't have to go hunt for it inside of the build product directory. On Windows, we do the same thing, except at least for this tutorial, we've been using the MinGW 32 setup with Anaconda, just because for the purposes of this tutorial, that's the most straightforward way to get things working. There are other compilers, many other compilers you can use on Windows. This one is falling out of favor, but for the purposes of our tutorial, it will work just fine.
Actually, I have a question about the C compiler. So, maybe this is more of a setup question, but so does setup know that you, 1, have the C compiler installed on Linux and Mac system, and 2, where to go find it?
So the question is, how does the setup PyScript or distutils know about C compilers, that sort of thing? So the answer on Mac and Linux is that you need to have a standard GCC C compilers installed beforehand. And distutils, when you run this command, Python will reach into the distutils module, it will go try to find a compiler, and if you have a standard compiler that's available on your path, that sort of thing, it'll find it and use that for compiling this extension module. So again, on Mac, if you're using Macs, then the standard thing is to install the developer tools, and that will work just fine. On Linux, again, you would just install the standard compiler package from your package manager system. That will also work just fine. On Windows, there are more compilers, more options for you. There's a Visual Studio compiler, there are some SDKs you can use, that sort of thing. But again, the same process is occurring each time. Distutils tries to find a compiler in standard places. First one it finds, it'll use and compile things for you. So when we have compiled everything, we'll have an extension module, and we'll see that in just a little bit. And then we're able to import that directly from Python. We can say import fib and fib.fib, call it, that sort of thing. It acts and looks and feels just like a regular Python extension module. There's another way of interacting with Python code, and this is more for just interactive development, not necessarily for distributing code. But it's this package called pix_import. And it allows us to import a Python source file as if it were just a regular old plain .py Python module. The nice thing is that it automatically detects changes in the Python file, and it'll recompile if it needs to. If it doesn't, if there aren't any changes, then it will load a pre-cached version of this compiled thing. Okay? And it's great for interactive development, for trying things out, making changes, testing, that sort of thing. And we'll see that also in our exercise here in a bit. So we have this import pix_import call at the top here, and we're just saying pix_import.install to get it set up. This will hook into Python's import mechanism. So now it allows us to say from fib import fib, or just import fib, or that sort of thing. And if there's a file called fib.pyx, pix_import will recognize that, compile it behind the scenes, stick that extension module somewhere, and then import that extension module for us. So it's all kind of going on, taking care of the compilation step for us automatically. And then lastly, the third mode of interaction with Python is with IPython from an IPython notebook or Jupyter notebook. The main entry point for that is the %% magic command. You can use the %% command. This is an old notebook, but it would still apply here. You can tag a cell with that magic command, and Jupyter or IPython will treat that cell as Cython code. And then when you execute that cell, it will, again, compile it behind the scenes automatically, load everything from that extension module for us, and then we can just use the Cython code from within that cell elsewhere in our notebook. So again, this is pretty nice, and it uses nice syntax highlighting too, so it gives us nice looking Cython code, that sort of thing. So you can integrate Cython with your IPython notebooks. So the PIX import in the IPython notebooks, it's doing the compilation work for us. So you have to keep that in mind, that it's doing a lot more behind the scenes. And for that reason, it can be really handy, but it also means you don't have quite as much control over the process as you do with the setup.py option here. So this one gives you full control. You can add extra arguments to your setup command and to Cythonize and that sort of thing to control exactly what compiler flags are used and that sort of thing. Okay. So we have an exercise just to kick the tires. It's the Hello World exercise. I'll show you where that is. Anyone see that okay as a font size, especially for those in the back of the room? Thumbs up? Okay, good. So here I'm inside of the unzipped directory that I pointed you to. And again, for those of you who came in late, I gave you pointers to the course material, the tutorial material on the email list. It's also on that GitHub page. It's just the latest on Master. So if you git pull or that sort of thing, you'll have the latest material. And I'm going into the exercises directory, and then I'm going into 01 Hello World. Okay. And in here we have 3 directories, just showing you the 3 main ways of interacting with Cython. Okay. We'll look at the first one here, the Hello World distutils. And I've got a README here if you want to read about it in depth. I'll just walk you through it here as well. But I'd like you to just to explore around, look at the files here, especially the setup.py script. And we have basically those lines we saw in the slides. Right? We have some stuff from distutils just to get the setup command, and then we have the Cythonize command. And then we're just calling setup, and we're using Cythonize to generate everything we need for distutils and setup to work. So we use this magic incantation, Python, setup.py, build ext -if. The -i says put the results in place here in this directory. F says force, so it says don't look at timestamps, that sort of thing, just recompile everything, and that's just a habit of mine, just to make sure I'm always recompiling each time. So when I run that, and that's what's in the make file as well, so you can just type make to do the same. You'll see a bunch of output, and I'll just point this out once, but we have a number of things output here. Here we have a line Cythonizing Cython, where'd that go? Cythonizing Cython hello world.pyx. So that line there is Cython telling us it's compiling the pyx file into a C source file. So that's the first compilation step. And then after that, it's distutils kicking in and saying, here's a .c extension module. I'm going to compile that into a Python extension module for us. So there's 2 calls to GCC. This is the first one here, just creating an object file for us with the right flags and everything. And this is what distutils brings us. We don't have to worry about the platform-specific flags, all those really ugly, nasty things to make sure we're linking in the right libraries and the right flags for our platform, that sort of thing. It handles all that for us. And then the second line here is taking that object file and creating a shared object extension module for us. And its name is going to be Cython hello world.so on Mac and Linux. And then it will be, for those of you on Windows, I'll get to you in just a second. It's just slightly different. But when this runs, the money is getting this .so file, okay? And we said in place, the -i flag said to put it here in this directory. And then we can, well, I have a test script here. And all it does is defines a Python version. Well, actually, let's just look and see what's inside there. It's just a very simple add function. Takes two C integers. Well, it'll take two Python integers, convert them into C integers, and just compute some simple expression. So nothing fancy here. Okay. And then inside of our test script, we define pyadd. Of course, just a pure Python version of this. Sorry. And then we're just running some timing code to compare the time, the performance difference. And you may have already done this, but just going to run the test code here. And we see that for this simple little function, just takes integers, computes some simple expression. The Cython version, is about 3-ish, maybe 2 to 3 times faster than the pure Python version. Okay. So we're getting a little payoff. We'll see much more dramatic improvements down the road. But the nice thing is, one, Cython, it integrates with Python. It lets us compile to an extension module and treat it just like a regular Python extension module, the end result. And we're definitely seeing already for this simple typing information, just adding in some simple ints, that sort of thing, we're getting some payout in performance right out of the box. And for a simple little function like this, where there's almost all, just call overhead, not much work to be done in the function, and then returning a Python result, there's a lot of overhead in that just converting between Python and C. So we're not going to be able to see a massive performance improvement. But for functions that are doing more work, we're often able to get much better performance improvements. And we'll see that in a little while. For those of you on Windows, there's a bat script here, build.bat. And it just is running the right setup.py, distutils incantation here to get things to work. And again, I'm assuming that you're running with the setup that I described in the email thread. So we're using the mingw, the compiler setup here. So you can just run the build.bat script to get the right results. You should see a Cython hello world.pyd as a result, and you should be able to run the test hello world.py script also. And again, you should be doing that from within the Anaconda command prompt. Whoa. It's way too big. Still too big. So here I'm inside of that directory in Windows using my Anaconda command prompt and getting it will also run the same steps basically, and the result will be this Python hello world.pyd. That's just the name of an extension module on Windows. Okay? And if we look at the output here, we see this PYD file. We can run it as before, Python test hello world.py. And we see about the same 2 to 3 factor speed up here. Okay. All right, so encourage you to move on if this is slower than you'd like. Look at the other components here. The second version is using pyx import, pix import to run things. And the important one to look at here is the use pix import.py. So you'll notice here that we have the same Python hello world.pyx, that's our Python source. We have a test hello world.py. We don't have any setup script anymore, right? We just have this use pyx import.py and this Python file. It's really all you need. Okay. So if we look at use pix import again, the top here we have import pix import and then pix import.install. This again allows pix import to intercept import calls to determine if the thing you're importing is a Python extension module or Python source code. And we can just run that. We can say Python use pix import. And it works. We don't see really any indication that this is Python code. Okay. There's no build products, there's nothing going on here. What's happening, of course, is that behind the scenes, use pix import is compiling this on the fly, sticking the results someplace, and then importing it for us. Okay. Let me, let's put an error in here just to show you that it is indeed doing something. So I added an error. I give it a type foo, which of course isn't valid. And we try to use pix import, and we get this error here. So we are seeing that it's picking up the changes, detecting the error, giving us some output here, and we're getting this big nasty import error. Okay. So, and if I fix that command, we can now use it again, and it will run with the latest and give us the some appropriate output. Okay. So again, pix import's doing a lot for us here. If for some reason it can't find a compiler or has some other configuration issues, you'll get some error. So it's because it's trading off control for convenience. Oftentimes it's a little bit harder to get it working. You can tell pix import how to find non-standard compilers and that sort of thing. For instance, on Windows, you may have to do that. I can show you if you're interested in pursuing this more. But again, this is more for just interactive development, just to build up a PYX file and just try it out in places. Not necessarily for distributing to people, that sort of thing, because pix import is doing so much more behind the scenes. And then lastly, we have the Hello World IPYNB, so the IPython notebook. So we can fire up an IPython notebook. Again, I'm inside of our 03 Hello World IPYNB directory. And we can load this notebook now. And let me and we have a number of cells here. Just some descriptions, that sort of thing. So we can execute these cells. First thing we need to do is load ext Python magic. So we're loading this extension, which will give us access to the Python command. And then here we have our familiar add function now. But we're, of course, tagging this cell with the %% magic command to tell IPython to use Python to compile this thing. And when you execute this cell, if there's an error, you'll see a big nasty exception. there's not, it'll just run as if it were just regular Python code. And now, since mine ran and it worked, we now have an add function to use. We also define our pyadd as well. And then down here, I'm going to just do time it on add and pyadd. So this is nice. It gives us the ability to interact with Python from within IPython and Jupyter notebooks. And again, it's doing a lot for us behind the scenes. So, you may have to do more work depending on your platform and your setup to make sure you're finding the right compiler. There are more options you can give the Python command to control those sorts of things. I won't have time to go into it here, but I can certainly sit down with you later if you're having issues. And it's nice. It integrates nicely with IPython. So any questions on this exercise? If you're having any issues, I'm happy to sit down with you later, but we won't quite have time to go into them with you here. Yes? You're on Windows? What is the error again? Doesn't ring a bell. I'll have to sit down and take a look with you. And is that, which example are you running? Is it the, just the distutils version or the, is it distutils or piximport or IPython? Piximport? Okay. Yeah, I'll have to take a look. Yes. So you're saying that when you run the timeit commands, the slowest Python version takes 3 times longer? It may be because, and is this for the notebook version or the piximport version? Distutils and notebook. I'm not sure if you run it a second time, it still does it. Yes, there's definitely some caching and possible compilation things going on already, although it's with distutils, yes, and I would expect it a second time to take care of that caching question. I'd like to sit down and take a look at the break, perhaps, to get more info. Other questions? Okay. So let's continue. So let's open up the Python language, talk about it in more depth. The main thing you'll see in Python is a cdef keyword. It's a new keyword Python introduces, and it's our kind of gateway into C from Python. And you'll see it used for declaring local variables inside of functions. So cdef int a, b, and I. The type here is usually if it's a valid C type name, then that's the type. It's a C type that we're declaring here. So we're saying a, b, and I are all C integers. The argument here in fib we declare as an int. We don't use cdef there, but conceptually it's the same thing. We're giving it a C type for this argument. You can also declare functions to be cdef. Talk about that a bit more in a couple slides here. But this creates a C function in Python. So you have regular def functions. Those are just regular Python functions that Python can work with. If you declare a function instead cdef, you're declaring a C function even though you're using kind of the Python-like syntax. And you give it a return type, for example. So here we're saying the C return type for this function is a float, a C float. And we're saying, it takes 3 float arguments, or 2 floats and an int, Notice here it's actually taking float pointers. These are kind of really C-style arrays, x and y, and then their length n. And then in the body of this, we have another kind of local variable declaration. We're statically typing. And here we're using a different form of the cdef command. We're using cdef colon and then an indented block. And this is really just to nicely group things. You could have cdef int I and then cdef float d, but you can group them like this if you have a whole block of declarations. And some people like this, groups things a little more nicely. But here we're just creating an int, declaring an integer, declaring a float, giving it some initial value. And then we're just walking through, taking the sum of differences, sum of squared differences, and compute the distance. And then lastly here, we're talking about extension types. So you can declare a class cdef in Python, and this will create for us something known as a Python extension type. We may have time to get into these towards the end of our tutorial here. But again, just to point out another place where you can validly use the cdef command. And what this does, creates something that's very much like a class in Python, but it's actually known as an extension type, which is a more fundamental thing. It looks and feels just like a regular class here on users, but you have much more lower level control at the C layer about what's going on, what data is inside of that, the instances of these extension types, that sort of thing. Then inside the body of this extension type, we can declare some C types with cdef as well. And this is more along, these aren't class variables, aren't class level things. We're declaring, kind of like in C++ style or Java style, the instance attributes for instances of this extension type. And so we're saying every particle has a position PSN array and a velocity array. And every particle also has an integer ID. Okay. So we have to do this up front because this is a C-level thing that we're declaring here. Python and Python needs to know how to arrange things at the C level when we do this sort of thing. But again, this is Python allowing us to control classes and extension types at the C level with a cdef keyword. Just a few more cdef declarations you can use. So we've already seen you can do declaring integers. You can do multiple declarations on one line. You could declare pointers. You can declare C-style strings, so a char star to S. You can declare float with initial value or double with initial value. And again, to point out that when you have some C type that overlaps with a Python type, the C type takes precedence. Okay, so this is a C float that we're declaring here, not a Python float. But down here, this line here, we're declaring a list, cdef list names. So we're telling Python we want names to be a Python list. And the nice thing about this is Python, if we know for a fact that names can be and should only be a list, we can declare that to Python. This is just regular Python list now, but when we interact with names, Python knows it's a statically declared list. So it will only ever be a list. It can only ever have list behavior, so I can shortcut and directly call code rather that's list specific. And so Python will be a little bit more efficient with using names rather than just using some general Python object. So for instance, if we say names.append, at the C level, Python will generate faster code because of that, because it knows names is a list. If names was just a regular Python object, and we say .append, it'll still work just fine. Python can work with regular Python objects, but when it'll have to do a more general lookup process to find the append method on some general names object and that sort of thing. So when you declare Python types statically to Python, you're giving Python more information about what it can do, and it can often generate faster code as a result. And also there's also some type safety you can get from this. If you try to do something on names that isn't a valid list operation, Python can often give you compile time error and that sort of thing. You can also declare dictionaries and just standard built-in built-in types with Python. Here we're initializing it to an empty dictionary, for example. And then lastly here, you can declare things as objects. And that is really not much different from just using an untyped, a dynamically typed thing. But at the very least, this gives us a reference counted thing to work with. So Python's very general in terms of the sorts of static declarations it can handle, both C and Python. We mentioned cdef functions. We'll talk about the three different kinds of functions Python supports here. So there are three ways we can declare functions in Python, kind of depending on what you want. Def functions work just like regular Python functions. They are just regular Python functions to Python. So here we have distance. It's a def function, so it's just regular plain old Python function. It expects Python objects as arguments, and it returns Python objects as a result. A cdef function, as we mentioned before, it's a C function that we're declaring in Python using Python syntax. So here we're saying distance is a C function that returns a float value and takes two float arrays and has an integer length n. And then same code as before, and we're just returning D as a result here. And lastly, the important thing to note on this slide is that cdef functions are local to Python only. You can only call cdef functions from within other Python code. You can't access them from Python. And there are reasons for that. They're meant to be kind of internal helper functions for other Python code. They're very fast because there's no Python overhead. If you think about it, a cdef function takes C arguments and returns a C data, so there's no converting between Python and C going on here. There's a third kind of function we can declare, a cpdef function, and these exist to kind of get the best of both worlds. They allow us to call a function from Python or Python, depending on where we call it from. I guess I should say, cpdef function, you can think of it as generating two functions for us. One is a C-only function that's very efficient when you're calling it directly from Python code. The other is a minimal Python wrapper around that C function that will allow this function to be called from Python. And it will take care of all the converting from Python to C and C to Python. So we have a distance function. The arguments here are what's known as type memory views. Don't worry about this for now. We'll talk about those later on. These are just really high-level array-like things we can use and work with from Python. And we're returning a float here. Okay. The important thing is that the arguments and the return types need to be compatible both with C and Python at the same time. So they're a bit more constrained as a result. But we just have body of our function here doing the same thing as our distance above. We'll see what this is like in a little bit. Yes?
So the cdef function just now, you're still using a Python syntax, but you don't have access to things like NumPy.
Good question. So question is, the cdef function, you're using Python and Python-like syntax, but you don't have access to NumPy. You actually do. You can call and use, it's not like Python constrains you to use only C compatible things inside of that code. You can use Python things in there. It's really just the interface to that thing. It needs to be, take C types as arguments only, so pointers and C values, that sort of thing, and return C data as well, because it's going to be called and used from C. Internally, you can do computations in NumPy, use any Python library, that sort of thing. You can create Python objects in there as well. It's just that it's really just what Python generates for this, and it generates just a plain C function for you that can only be called from C. But it's a C function that can still interact with and use Python things internally. Other questions before we move on? So again, talking about just an example here of using def and cdef functions. So here on the left we have two little functions, an inc function and an inc seq. function. Inc is kind of meant to be an internal function that just very simply just adds two numbers together and returns them. Inc seq just walks through a list, calls inc on each element with some offset, and then builds up a new list result out of those. Okay, so inc seq is an outer function that's calling inc internally. If this is, and this is Python code, you can tell, you know, because we're typing here instead of inc, so this isn't valid Python. But if we compile this all together into an extension module, we can now call inc.inc, and we can also call inc.inc.seq to access both of these functions here. Nothing fancy or surprising going on here at all. Over here on the right, we have the same code, except now inc is renamed to fastinc, and it's a cdef int function. Okay? So again, this is a function that only lives at the C level. It adds its two integer arguments and returns an int. When we call fastinc now from fastinc seq, this works because it's all inside of the same Python source file. Python can access other cdef functions, no problem, but it's not exposed to Python. We can't call inc.fastinc from external Python code. But we can call fastinc seq because it's a regular def function. Def functions are just available to be used from Python or Python code. Okay. So this will be, as indicated by the name, it will be a little faster because there's less going on here in terms of converting and that sort of thing. Python's able to generate code that's much more efficient. There's much less call overhead when you're calling fastinc. But again, we also mentioned the cpdef function, and we can declare fastinc cpdef, which allows us to both call it efficiently from within inc seq here, and it also allows us to call it from Python. Okay, so this gives us the ability to call from Python and call efficiently from Python. Okay. So these three functions, def, cdef, cpdef, the three different kinds of functions in Python, def are just regular Python functions meant to be called from Python or Python, no problem. cdef functions, they are available to be called from Python only. They're more efficient. They have less call overhead. cpdef functions give us two functions for free. Okay, we declare it once, we get two functions, a C function that's efficient, and then a minimal Python wrapper that allows that C function to be called from Python. Good question. So the question is, why wouldn't you always use cpdef? I mentioned earlier that cpdef is a bit more constrained in the types of arguments it can take. And these have arguments that are both compatible with C and Python at the same time. For instance, you cannot declare a cpdef function that takes a pointer, a C pointer argument. So if you know you want a function that interacts heavily with C data types that aren't also compatible Python data types like pointers or C arrays, that sort of thing, you would need to use cdef for those sorts of functions. But otherwise, you often use cpdef pretty frequently, unless you know you need stuff that's specific to cdef, just working with C directly. Another question? Yes? Is cpdef any less efficient than cpdef? There's, you know, if you're talking like probably microsecond differences here, because when you're calling a cpdef function from Python, there's a wrapper function that you're first calling, and then it calls the internal C function. But the overhead from converting the Python types to C types would definitely dominate that time. Calling that little C function would not be much overhead at all. So it'll be tough to notice a difference. There are situations where the performance does pop in, but we won't have a chance to get into the very kind of side things. Other questions? Yes? Good question. Overloading. That's definitely outside the scope of this tutorial. Yes, you can do overloading. And that's a case where cpdef comes in. You can have not to get into too much details here, but I can sit down and talk to you about it as well. So the question is, do you have to type the output of the cpdef function? You don't actually. If you leave off the type, it will implicitly type it as an object type, a Python object type. So in that sense, you'll be kind of creating and returning a Python object as a result here. Okay? But often with cpdef, you will declare the type if you know. Like here, for instance, there's no reason not to declare the return type as int. So you could just use it as a regular C function later on. But yeah, if the return type for cpdef is optional. If you leave it off, it will just assume a just general Python object as a result. The question is, how do you debug Python? It's a good question. I'll touch on it a little bit later on. It's everything from, of course, there's just regular plain old print statements, right, which can get you so far, but not all the way. There has been work in creating hooks into GDB to allow you to debug Python from within a GDB session and be able to jump between Python code and down into Python and back and that sort of thing. It's definitely a more experimental part of Python to generate that. Hasn't been actively developed, so it's not as up to date as it could be. But you can also just use plain old GDB with an extension module, and it's not nice because you're in the C layer and it can be kind of ugly. But often the best route is to get the Python version of it working well, and then convert that over to Python and have, be able to go back and forth between the Python and Python versions. But your standard GDB and C compilers will allow you to generate debugging information and that sort of thing. Okay, next exercise, typing. It's going to be playing around with adding type information to Python code, that sort of thing. So I'm in the 02 typing directory. And we have two subdirectories, Hamming distance and Levenstein distance. So first go into Hamming distance. We have a number of files here. You can look at the README. I've got everything kind of spelled out there. But let's look at Hamming.py. So inside of Hamming, we have two very simple little functions. One is Hamming sum, takes two arguments, two strings, S0, S1, and then Hamming loop. And they're just two different implementations of the Hamming distance calculation. Hamming distance is nothing fancy at all. All it does is just walks down two strings. First checks to make sure the strings are the same length. And then it just walks down them and just adds up, tallies the number of spots where they differ. That's it. Okay? So it just says, for each pair of characters in these two strings, are they different? If so, okay, add one, and they return the result. So just the number of spots where these two strings differ. And here we're using just a nice high-level sum function with a generator expression and the built-in zip function to just zip things up, walk through them, and compare where they're different, and add up the number of spots where they're different. Okay? Nice high-level Python code. And then down here we have a big ugly for loop. Right? Those of you who have used Python, you know this is definitely a code smell, not Pythonic at all, and that sort of thing. So we have both versions here to kind of just illustrate kind of the trade-offs you make and the sorts of patterns you use when you're taking Python code and you're converting it to Python and speeding it up with Python. So here we're just walking through, again, an integer index into our strings, and then just adding to count the number of times that they differ. So same computation as the Hamming sum, but just using a for loop instead. Okay? So that's Hamming.py. And then all I've done is just copied that into Hamming.CYTHON.pyx. So it's identical right now. We're going to be modifying this file to add in information. Okay. And first thing I want to emphasize is that that's just regular Python code. We don't have any specific typing information in there at all, and that's fine. Cython works with almost all Python code is valid Cython code. Python language is always changing, and so Cython's just a little bit behind. There's some constructs it has trouble dealing with, but they're very small and they don't pop up very often at all. Cython handles generator expressions and decorators and all kinds of fancy things very well. So Hamming.CYTHON right now is just a plain old Python code just dumped into a PYX file. Okay. Then we have a solution file, which is kind of the end goal of this. You can look at it if you want. You can nod if you want to just try to get there on your own. But we have a setup Hamming.py. It's one of these distutils scripts, and we're just compiling two extension modules, each one into its own, compiling two Python source files, each one into its own extension module, using Cythonize here. So we can say Python setup Hamming.py build ext-if. It's going to compile everything together. And that's done, if it's successful. Again, if that went too fast, just called Python on our setup Hamming.py. Build X, that's the command we're giving distutils, and -if, I is for in place. It says put the extension modules right here when you're done. F says force it, so even if I've already done this before, ignore all that stuff, just redo it. Okay. And you'll see all the ugly output, and then you'll get Hamming.CYTHON.so and Hamming.CYTHON.solution.so. On Windows, again, you feel free to just run the build.bat script, or you can type in Python setup Hamming.py build ext-if-c mingw32. Okay, so the only addition is this -c mingw32 to tell it which compiler to use. Yes. Yeah, so a question about warnings and warning suppression. You can, I won't quite have time to point out where to do that here, but you absolutely can give any and all extra compiler flags to suppress those warnings, that sort of thing. Yeah, for now we'll have to suffer through them, but I can show you where that is. Okay, so when that runs, and presuming it's successful, we have these extension modules now. And if we look at test Hamming.py, all we're doing is just using timeit in kind of the low-level way to run the Python version of it, the Cython version, and the optimal or the solution version of Hamming sum. Okay? So there's Hamming sum, and then we also do the same for the Hamming loop functions, just to compare. So if I say Python test Hamming.py, it'll churn for a little while. I believe they're running for 1 million iterations or something like that. And so you see each step there's a little bit of speed up for the Hamming sum stuff. So you see our Python version is 1.7. The Cython version, again, that's just we just copied Python to Cython source file. Didn't touch the code at all, right? So we get a little bit, about maybe 10, you can expect 10 to 20% speed up, very, very roughly, just by compiling this code rather than just running interpreted Python code here. And then the optimal version of this is a little bit better, but still not much. We're in just the percentage range, not order of magnitude range, right? Now here, the loop version, we get much bigger differences. So again, the Python loop, interestingly, the Python version of the loop is faster than the some version, although I wonder if that's just related to the inputs we're using. The Cython version is already, again, this is not even using any type information yet. You know, it's a factor of 3, 4-ish, 4 to 5 faster. And then when we add in some more type information to get this optimal version, we get another factor of, 4 or so out of it. So we're getting pretty significant speed ups with this loop version. So your job, feel free to do this while I kind of talk over, is to go inside of the HammingCython.pyx and refer to the slides that we went through as well. And think about, where can I add type information? Honestly, for now, I would ignore Hamming sum. I would just focus on Hamming loop, because things are kind of broken out there a bit more. There's some obvious candidates here. A rule of thumb is to, count is obviously an integer, so we can obviously type that pretty easily. The other things that are important are to make sure you're typing the loop related variables. So we want to make sure we type the loop variable I here, want to give it a type. And also we want to make sure the argument to range has an integer type as well. So whenever Cython sees for loop variable in range some integer, right, and the loop variable and the argument to range both are integer type, then Cython can generate a very efficient loop for us. There's no Python objects involved here. It recognizes that as a pattern to use to generate just a very efficient C for loop, so there's almost no overhead now in the loop. And then we just want to make sure also, as best we can, that the body, the variables and the things we're using in the body of our loop are also typed. So again, that count, we should type count. And S0 and S1, that's a little trickier. There are some hints on the slides for how to type those to give them some valid C types here. Question? Yes? Question is, does Cython care about range and X-range? X-range will work in Cython. I'm curious, though, what it does with X-range, if it treats it specially or not. I've only ever used range because I know it recognizes the pattern for I in range n or something like that. Cython will be safe for you, if you're using anything fancy. So I would, by just guessing, I would expect to treat X-range as a generator and perhaps just call it one after another. But maybe it short circuits that as well. I'm not sure. Yes.
More generally with generators in Python 2, still Ample is pretty friendly, so you change that zip to be an intertool to izip, etc.
Good question. So question is, if I change the zip to itertools.izip, will Cython do anything special there? So it will work, first of all. It won't break, right? You can import and just use regular Python stuff in Cython. That's no problem. It's more a question of, does Cython recognize zip and generate different code than if you were to, or does it just call into the built-in zip? To answer that definitively, I'd have to look at the generated code to say. I know that since this Hamming sum function never really gets much better performance than the pure Python version, it's probably just treating it generally. It's probably just calling the general Python zip, looking it up in the built-in namespace and using it there. So if you use itertools.izip, I wouldn't expect it to do anything special there either. It would just call the same Python function ultimately.
And more generally, how does Cython play with Python 3?
Good question. So question is, how does Cython play with Python 3? Let's wait till the end of this exercise and I'll talk about that quickly, but it's an important topic. So I'll touch on that a little bit. Okay. So, yeah, so if you're using, show of hands, who's using Python 3 here? Okay, handful of you. Sorry, I should have prefaced things by saying this is all tested on Python 2. You can absolutely get Python to work with Python 3. It has a lot of nice extra features to work well with Python 3. Of course, as we know, talking about Python 2 versus Python 3, strings, of course, are the bane of our existence, right? There's going to be lots of things surrounding strings. And Python has lots of tools to help us deal with strings so that we can have a single source file, single Python source file, and it can work with Python 2 and Python 3 depending on just how you compile it. Okay, so, and it has, let's see. So one thing you could do, you could declare these as bytes. I'm curious if that will work. Just to tell it, because bytes, of course, is the type that's valid Python 2 and Python 3. Python will now know this is meant to be data, not meant to be Unicode strings or depending on the version of the language. Let me just try that quick. Looks like it's working at least for my Python 2 version. Did that work for you? Did you try that? Or? The third one in the solution? Oh. Gotcha. Yeah, you'll have to tweak the... Yeah, you'll have to tweak the solution file as well. Or I guess you could, inside of the test-hamming.py, you could tweak that to, instead of strings over here, you could make byte strings instead, so you're passing in bytes as arguments rather than just, you know, Unicode encoded, Unicode strings here for Python 3. But I'll touch on Python 3 in more depth after this exercise here. Passing bytes does work. Okay, good. Like I'll update the exercise for after the tutorial as well. All right, so hopefully you had some time to think about what types to add. So let's do that quickly here. Hamming.python.pyx. So here I'm just going to type count as an integer, right? So cdef int count. And I'm also going to type I as an integer, cdef int I. You can also say, one more thing, we want to make sure that range, the argument to range is just a plain integer as well. So we're going to take that argument out and say, cdef int n equals len s0, and then put n here into range. Okay. And we made the arguments bytes just for Python 3 to be friendly with that. Let's just see what the performance is with this guy.
Just out of curiosity, that len
Yeah.
is actually looking for a null terminated string. Is that what's going on there? How does it know the length of the array there?
So at least for these versions here, for this version here, S0 and S1 are Python bytes, byte arrays, right, byte objects. And when we call length on that, it's just using the Python length built-in function to get the Python length of that string, right? So if there are embedded nulls, right, that's fine. Python strings have, you know, the data and the length that's separate, right? It's not like a C string that walks through. hold on to that question. I'll point out where that's relevant in just a little bit, the null terminated stuff. Okay. But for now, because we type these as Python strings or bytes objects, the length is kind of the Python length here, right?
So when you define those as char stars, those are also Python.
No, that's I'll get to that in just a little bit. Yeah, I'll get to that in just a little bit. But it's a very good point. So Python, let me just call make here because it's got everything together, and I'll run the tests. Okay, well, performance didn't change that much. Let's see here. Interesting. So it's looking like that was the key. Yeah, I appear to be doing the same thing. Let's see here. There we go. So that was the thing holding us back. So let's talk about that then. So Hamming loop started out with two arguments, S0 and S1. They were untyped, so that means they're just general Python objects. When you interact with them, Python is forced to just do general Python operations. At runtime, it has to look up attributes and functions on it, that sort of thing. So it's kind of like runtime overhead when you're interacting with these things, but of course they're very general, very flexible. Here, we did a kind of intermediate step. We declared them as bytes. So it's statically declaring them as a Python type. So Python knows these are only ever going to be bytes objects. So it can be a little bit more efficient that way, but it still wasn't much of a performance difference in the end. Then we went down all the way to declaring them as char stars, so C-style strings here. And you notice that we can still call len on, so we changed it from a Python type to a C type now. So you can pass in a Python string or Python bytes to one of these, to Hamming loop. Python will extract the underlying C string from that Python string and use that internally to the function. We can call len on that thing now, but that's actually going to be calling strlen under the hood. Okay, so if you know anything about C strings, they're null terminated. And so strlen will, of course, walk through the characters until it finds a null byte, and then that will be the length of that string.
And that's safe from blowing up because you're converting from a Python string to a character string.
Correct. It is safe from blowing up because Python strings are null terminated. So, but the one case where they will differ is if you have an embedded null character inside of your Python string. Python, that's allowed in Python strings, right? Because Python strings have a separate length, separate from the string data, right? But strlen will be fooled by that. Because strlen, like C strings don't have any separate information about how long this thing is, right? So there is definitely a difference there. That's something you need to keep in mind, right? You might, to be safer about this sort of thing, you might have a wrapper around this to look at your strings and see if they have embedded null characters, and if so, have like a fallback version or who knows what. But you could detect that first, and then if you know it's safe, there aren't any embedded nulls, then call your fast version here. But yeah, that's definitely something to keep in mind. We're now working with C strings, so all the speed of C strings is what we get, but the trade-off is, of course, the cruftiness of C strings here. How does it behave with Unicode? So here we're just using them as data strings. So just this will work out of the box with Python 2 strings or Python 3 bytes objects. This will not work with Unicode encoded strings. Python will complain if we try to call it with those kinds of strings. So we're using strings as kind of like data buffers, more or less. We're not treating them as like string data that needs to be encoded and decoded and that sort of thing. Won't have time to get into it, but you can tell Python to work with Unicode strings and has facilities for working with that well also. But just to drive the point home, we have our typing information inside of the function as well. And we have our for loop now, which has the loop variable is typed, the argument to range is typed, and everything inside of the loop body is also typed. Okay.
So would it be more efficient to have it setting n ahead of the link comparison? Because now you're doing the string twice.
Oh, good question. So question is, would it be more efficient to put n up here and then use it inside of the length comparison, for example? Yeah. Yes, it would be, because now since our strings are C, or char stars, each time we compute the length of a string, it's an order n operation, right? We have to walk down that string, find the null character, and count up the number of spots. Yes? Yes. Yes, you could, absolutely. Yes. You're right. Yeah, absolutely. So the question is, couldn't you be a bit more clever and just use the fact that your Python string already stores the length with it, so you don't have to recompute this every time? Absolutely, you could. We just didn't do that in this exercise here. So yeah, you could extract that information before you extract you could just pass in S0 and S1, and just to show you what it would look like a little bit quickly. Yes. Okay, yeah, it's definitely something, like if you look at the generated code, when you type something as a char star, it's forced to use strlen when you get the length of that, because it has to assume it's just a C string and use that. But I didn't quite catch all of your statement, but yeah. I see. So you're saying, I see. So if you typed up just the arguments and just the result, then you'll get the same speed up. So basically, just giving it the information that these are char stars is sufficient to get this the speed up that we're looking after. Yeah. Okay. Yeah. The point is definitely taken. Let me get back to that in a little bit. Let me just finish this one thought here first. So we could just leave the arguments as Python strings, S0 and S1, and then have internal variables, C0 or CS0 perhaps, equals S0 and cdef char star CS1 equals S1. And then we can use S0 and S1 as Python strings and get the length on those, and then use CS0 and CS1 as the internal, just extracted C strings to interact with, which are going to be much more efficient. Okay. That would work just fine. But to your point about you don't even have to declare this internal stuff, so Python actually does have type inference. And it's pretty good. It's getting better and better as time goes on. We have the ability to go in and declare things as we did here, like cdef int count. But Python's smart enough to realize, oh, okay, count equals 0, right, before we typed it here. So we don't ever actually change count's type internally. So it can figure out that count is only ever a C integer, okay, and give us the ability to not have to type it explicitly. Same thing with typing I and N. It can often figure those things out as well. I tend to put in, you can go at it incrementally and just type just a few things at a time and see what sort of performance boosts you get. You can also just go crazy and type everything and then remove types to see what things matter and what don't. In this case, making sure you type the arguments to extract this underlying C strings is really the important part. Largely, I would imagine, because inside of that loop, the expensive operation is grabbing the data out, and if these are just regular Python strings, there's much more general operations it has to perform to get the data out of those strings. Okay. Yes?
Are you going to introduce annotate?
Yes, it's a good time for it. So there's also this really handy thing in Python called annotations. So here I'm just going to call the Python compiler, give it the -a argument, and say Python-a, and then some Python source file. So Hamming Python solution.pyx. So this will, besides compiling into a C file, also generate an HTML version of this. So let's open that up, and we get this file that has the same source code with this color coding. And more or less, kind of the heuristic used here is the darker the yellow, the more Python operations are going on there, kind of very roughly. And you can expect the darker yellow lines to have more Python overhead and therefore, you know, more often than not to be slower than otherwise would be. And the nice thing is you can expand these lines to see all the C code that Python's generating here. There's just a ton of code generated for this sum function here. Because Python's generating a generator function on the fly and or, you know, for us in C and calling into that and that sort of thing. So there's a lot going on here. Let's see. Here's the Hamming loop. So you see at the def line, there's a lot going on. But the nice thing is down here in the for loop, if you look, here's the actual for loop body. There's lots of name mangling going on here, so it doesn't look very nice. But if you squint and if you were to look at the source code and see what the types of these loop variables are, you'd see that this is just a plain old for loop with integer, pix t6 is an integer, and the comparison here is just between integers, and adding 1 to it, of course, is efficient. And here, down here, at the count plus equals this guy, here again, we're just incrementing a count variable, and we're doing in C just a comparison between, you know, a character in a C string with another character in another C string. So it's translating into very efficient C code. So this is really nice. And again, the highlighting here is telling us, giving us clues into what code might be slow. Right? And it more or less is correct. Like it does a pretty good job of figuring out which connections, which lines are going to be bottlenecks. And of course, you want to zoom in on loops, the bodies of loops, that sort of thing, code that's going to be run a lot of times. So if we were to run this, let me just show you for comparison. So you can, as an aside, you can throw a .py file at Python. You say, hey, compile this Python file. And if everything in that Python code is supported by Python, it'll work. It'll generate C code for you and compile that. So we're just seeing what Python does with our Hamming.py file. So let's look at it. And you notice here, its annotated source file is much more yellow, right? And especially in the loop down here. You notice here we're getting PyObject length instead of range. And I'm curious, though. It might be generate some pretty efficient code here. I'd be curious to look at that. But here, instead of the body of the loop, we're definitely doing lots of Python operations. We're getting elements out of some general Python objects, doing a PyObject-rich compare to see if they're not equal to each other, and then PyNumber in place add. So lots of Python operations here, which is why this is darker yellow. Oh, so if the arguments were int star instead of char star? Unfortunately, no. Because this is a def function, They don't accept, so an int star would be a C pointer or a C array, and that's a C-only thing. And since this is a def function, that has to be compatible with Python. So there's no Python type that corresponds to that. We'll see in a little bit later on when we get to arrays how to have things that can work with both C and Python types for array data. All right. Some really good questions. Let me point out at least the other exercise here. I won't have time to go into it, but there's another file here, Levenstein distance. This is just another distance computation between strings, talking about the number of insertions, deletions, and changes in a string, so a bit more general. The computation for this, well, the goal, again, I won't have time to go into it, but look at Levenstein.py. There are three functions here. The idea here is to explore creating cdef functions and seeing what sort of performance improvements we get out of making functions cdef. So Levenstein distance is meant to be kind of the interface to this, the way we call this from Python, and it just calls lev with the string, its length, and string s, string t, and their lengths. And then lev just has this kind of recursive implementation here. Okay. This will come up later on in the other exercises where there's a much more efficient way to implement Levenstein distance rather than recursively. We'll talk about that with arrays later on, so I wanted you to at least see this. And then there's inside of lev, it calls cost as well, this little simple little cost function. And so the goal of this exercise, and I'll just show it to you, Levenstein-CYTHON solution, is to, so you see we keep our Levenstein distance a def function. So again, that's able to be called from Python or Cython. Right? This is kind of our external function that's going to be called by other Python code. And now we've made lev into a cdef function, and it's a cdef int, and it takes char stars and integer arguments, and then we just have three cdefs to compute the three different calls to lev, and then we just compute the minimum here in this if elif else block, and return the minimum of these recursive calls here. Okay. That's all that's going on. Cost is also made a cdef function as well to remove call overhead.
So you, here instead of in the not solution file, you use the built-in function, but here you just use the plus.
Yeah.
Are you able to use the main function, or just for efficiency here?
Good question. Yeah. So if you look at the kind of workspace, the Levenstein-CythON.pyx file, here you see we're using min, and so the question was why am I using min here, and why did I use an if elif else block on the other file? The performance difference for this change wasn't that big. I was just seeing if there was this tiny improvement, but honestly, if I were doing this for real, I probably would still just use min because it's much clearer. You don't have all this temporary stuff and this ugly if else block. But again, just to also give you an indication of the sorts of things, transformations you can make from high-level Python to perhaps lower-level, more kind of blocky procedural C-like code in Cython, and things to try out for when you're trying to get better performance. This particular attempt didn't really make much difference. Yes? So if you have an existing C++ source file and then interact with it from Cython, it's a perfect lead in to the next part. So yes, we'll be talking about that in just a little bit here. Okay, so that's just to point out this exercise of seeing the performance trade-offs when we so when we go from a pure Python version with all these recursive calls, the Cython version is about 2x faster already. And then when we convert those function calls to cdef functions, because there's so much function calling going on, in this example, that's where the bottleneck is. The function call overhead is really where all the slowdown is. So if we get rid of that overhead by converting these to C functions, then we see a dramatic improvement here, like a factor of 50-ish boost. Okay. Again, this is a very inefficient implementation of Levenshtein distance anyways, but we'll see a better version with arrays later on. Okay. So, any other questions with these exercises? At least it gives you a template, things you can explore when you're adding type information to Python code, that sort of thing. All right. Continuing on then. So there was a question about just interacting with external code from Python. This is the other main use of Python when you have existing C or C++ code and you want to interface it with Python using Python. And again, Python's sitting in that middle layer between Python and C or Python and C++. So it gives us the ability to kind of make, just work in either direction. So here, imagine we have existing C code. Here, well, of course, we have the standard C library, which has a lot of C code for us to use already. There's a string.h header inside of the C standard library. And the way we can expose, let's say we want to be able to call strlen from within Python. And we can do that by saying, we use a cdef extern from block here. So we say cdef extern from, and then the name of our header file, in this case string.h. Then we have a colon, and then in an indented block, we just declare the interface for whatever C things we're going to be using from that header file. We only have to declare the things we're going to be using. We can ignore the stuff we don't care about. But we do have to declare it. We can't, Python doesn't just automatically slurp in string.h and parse it for us and know how to interact with that. It doesn't have a C parser as part of Python. You have to tell Python the things you're going to use from this C library and their interface. So here we're just saying strlen is a function. It takes a char star and it returns an integer. And again, the thing to emphasize here is that Python, this is just exposing this C function strlen to Python. It does not allow us to call it from Python automatically. To do that, we have to create a def function explicitly to make that happen. So that's why we have this def getlen here. And the argument is a char star message. So again, we've seen that work with Python strings before. Python will extract the underlying C string from a Python string for us. And then all we're doing is we're just calling strlen with message as an argument and just returning that integer as a result. So we compile this all together into a len_extern extension module. And you notice here we can't say len_extern.strlen. We can't go in and grab that C function directly. This declaration here is only for other Python code to use. We have to create a def function, and def functions are visible to Python. Okay? And so we can say len_extern.getlen and give it a little string here and get back 7. Okay. So this is the basics. Yeah.
So, can you go back to this? So you're sort of telling it, like, go look at the string.h file, but then you're sort of putting in exactly what's in the header file in here. Why not just say, go look at the object file, there's going to be a function you want to use, and this is what it's called.
Yeah, so the question is, you're already telling it to go get the string.h header file. Why can't it just do the next step and look inside and just use that?
Well,
Or,
yeah, either that or just say, go look at the library file where the code's actually implemented and tell it this is the function that I want to call from that library file.
yeah, you absolutely could, and it would be a matter of just someone going. There's nothing preventing Python from doing that, other than just someone taking the time to implement that functionality and make it happen. There are probably other reasons that I don't know about for why they went with this approach initially, in part because they don't have to parse C header files, which can be highly non-trivial, right?
So, but I guess
Uh,
the cdef extern from string.h must be effectively some sort of pointer to the library file, because that's what it actually.
So actually, the only code that Python emits for this entire block is a pound include string.h. That's it. The declaration here in Sterling, this is just for when Python is generating a C file. It can check that when you're calling Sterling, you're calling it with the right type and you're using the return type appropriately as well. It's just type checking and make sure you spelled things right and that sort of thing. So it's just for compile time checking when Python is generating C code for you. That's all it uses it for. So, and people have asked for this a lot. This is in terms of just more automation for Python to allow you to at least automatically extract things from this, that sort of thing. There have been some attempts at this. The straightforward case is of course straightforward, but there are a lot of edge cases as well to consider. And again, to properly parse even just C header files is a challenge. So putting that in just will take some time. So that's my best understanding as to why it's not in there, more automatic. Other questions? Yes. Really good question. So mentioned that the side effect of this is if you wanted to have a Sterling function in Python, you would have to worry about name collisions and that sort of thing. I don't have the opportunity to go into it here, but you can separate out this declaration stuff into its own little file in Python, and then say C import that, and then you say like declaration dot Sterling. So that's your declaration of Sterling, and then you can have a Sterling Python function that's separate. So you can basically group this declaration stuff into its own little namespace, and so then it's unambiguous about what is the C stuff that you're declaring and what is the Python stuff that you're using or wrapping it with. Okay. Unfortunately, I don't have time to go into that here. Yes, question? Yes, absolutely. So the question is, would it be useful? People ask for this more automation here, and would it be useful? I think absolutely. It would. It's just a lot of work, a lot of thankless work to get this working robustly. But yes. Yeah, this definitely would take Python in more of a Swig direction to kind of automatically wrap a large code base in Python. And actually, I should mention, it just comes to mind, I totally forgot. There is a project that is taking this pretty far. It's called Crossstress or Xstress by Anthony Skopats. He's the main contributor. And it uses Python to automatically wrap potentially very large C and C++ code bases. So I encourage you to check that out, take a look at it. It's not part of Python itself, but it uses Python heavily to automatically generate wrappers for code bases. Other questions? Okay. So there's more than just functions in C. There's structs and type defs and that sort of thing. Python can handle those as well. Here we have a more involved, more interesting case. Let's say we want to interact with the TM struct from the time.h header, just part of the standard C library. So check the time here. Okay. Here we're saying cdef extern from time.h like before. So we're telling Python, I'm going to be declaring things from time.h. Python will only generate just a pound include time.h for all of this. So it's not this is really just, all these declarations in here are just to tell Python how to properly call and use these C-level constructs. Here we're declaring a struct to Python. We're saying there's a tm struct inside of time.h, and inside of the struct tm there are 3 integer fields, mday, mon, and year. There's many more besides this. I think there are like 7 or more fields inside of this struct. We only have to declare the things we care about, even inside of the struct body itself. Okay, so So that's nice. We don't have to tell Python that there's all this stuff inside of TM. We only have to tell Python there are 3 things I care about inside of the TM struct, and here are their types. Okay. This is declaring a C struct. It's just using Python-style syntax for that thing. Okay.
So you said this works with C++ header files too. Does it only support C-style structures or does it support anything with C++?
Good question. So the question is, I mentioned that we can also interface with C++, but the question is, can you only interact with C-style structs from C++? The answer is no. You can declare C++ classes to Python and interact with them, and Python knows about when you're in C++ mode, it knows how to interact with Python or C++ in more sophisticated ways and that sort of thing.
Is there any like STL support then? Can you figure that out?
Yeah, the question is there's STL support? Yes, there is absolutely. Python comes with a whole library of wrappers for STL containers and for a number of C standard library header files as well. I'll have some extra slides afterwards that are in the slide deck you have that go into that. And if I have time, I'll touch on that as well. How so? With Python specifically? So I've used Boost with Python, for instance, to bring in some smart pointers from Boost. We had a C++ code base that wasn't using C++ 11, so using Boost shared pointers, for example, from Python. So you can use templated types with Python. It has its own syntax for it, but you can absolutely use Boost and Boost style things from Python. When you get into really fancy stuff like template meta programming and that sort of thing, then you have to kind of smooth over the interface a little bit because Python doesn't know and doesn't need to know about any of the kind of really fancy Boost things. It just needs to know kind of what is the end C++ interface for this thing that but you absolutely can use Boost with Python. Yes? Question about exceptions. Yes, you can. In C, of course, doesn't have exceptions, so you have to do error checking. And so if you have a wrapper function and you detect an error code, then you raise a Python exception, right? In C++, you can tell Python, capture these sorts of C++ exceptions and convert them into an appropriate Python exception. And Python automatically does that in kind of intelligent ways already. So if you have like I forget the C++ exception names, but there's a fairly natural correspondence between like memory errors and I forget the C++ exception for that, but Python does a good job of converting those for you in an intelligent way. I don't have time to get into that though, unfortunately. So here's our struct. We're going to be interacting with that from Python. Here's a type def. We declare it with C type def here, but just a type alias, right? So time t is now an alias for long. And then we're saying local time and time are 2 functions. The local time takes a time t pointer, returns a tm struct pointer. Time takes a time t pointer, returns a time t value. And again, all these are just declarations. Here inside of getDate, this is the actual function we can call from Python now. And we declare time t here, a cdef, time t. And then we declare a tm struct pointer, ts. We call time with null, that just gets the current time. And then we call local time with the address of that result from time. And that gives our tm struct pointer. And then lastly, down here, we're just returning this thing, ts.tmmday, ts.tmon, so the day, the month, and the year, right? Now, if you look at that, you say, okay, that's creating a little Python tuple, 3-element tuple, and returning it. Nothing fancy, nothing surprising going on here. But the elements of that tuple are, of course, integers extracted from a C struct. So on this one line here, it's really interesting if you think about it. This is where Python's ability to blend Python and C is really kind of coming to the front. We're creating a Python tuple and returning that. But the tuple is made up of C integers that we're extracting from a C struct pointer. And if you notice, you're using struct pointer dot syntax, so you don't use arrow in Python. Python knows how to keep track of whether something's a struct pointer or a struct value and can generate the right code for us. But the important point here is we're extracting C integers from something and building up this Python tuple. The generated code for this is several dozen lines because there's lots of error checking, lots of Python objects being created, that sort of thing. This is really showing where Python's ability to blend these two languages nicely comes to the front. And of course, we can compile this all together. We can call getDate, and we get current date out of it. So the result is fairly boring, but the interesting part of is what's going on under the hood here, and our ability to interact with not just C functions, but C structs and type defs and all the things we would care about interacting with at the C level. You can even use like C macros, just treat them like C functions, for example. There's several other things you can declare and use here. So the question is, can you pass around the raw pointer to Python functions? Not directly, no. You can. It takes a little bit more effort. You can do it an ugly way by just converting that pointer into an int, right, a long or something, and give that back to Python, and then Python just holds on to that and passes it in, and you cast it back. You can't cast in Python between stuff. It's a little ugly though, right? It's a little, but there is another construct called a capsule in Python. It's at the C level. It allows you to have a valid Python object that holds a pointer to something, and you can pass that around in Python and hand it off, and then something can extract the C thing from that capsule. So yeah, you can absolutely kind of encapsulate things, give them to Python to hold on to, and then call something and extract it later. I would tend to use a capsule. It's much more recommended. It's much safer in a sense. You still have to know the type. Like inside the capsule, it just holds onto a void pointer. You have to cast yourself. But it's still, Python knows, oh, this is a capsule object. You can't use anything from it from Python. It's just an opaque thing. But at least it knows, okay, this is something holding on to something in C, so I won't do anything crazy with it. I'll just hold on to it and then give it to some C function to use later on. All right, we have an exercise. We'll get started on it, and then we'll take 5 minutes on it or so, and then we'll break. And then we'll come back and we'll wrap up this wrapping exercise. Okay. So hopefully you know where to look right as of now. You can go into the wrapping, 03 wrapping subdirectory. And then here we're going to be wrapping a C version of our Levenshtein calculation. So inside of Levenshtein.c is a C function that computes the Levenshtein distance, but it uses the array form of it, so it's much more efficient rather than the recursive calls that we saw before. Don't worry about the details. They're not important here. Really, we just care about the interface. Okay. So we take two car pointers, S and T, so two C strings, and return an integer, the distance between these strings for the Levenshtein distance. Okay. And you can look at the details if you like, but there's a Levenshtein.CYTHON.pyx, and I've kind of stubbed it out for you. So we have an empty wrapper function, Levenshtein distance, takes an S and T arguments. It's empty right now. And here we've commented out kind of a cdef extern from Levenshtein.h declaration thing. Okay, so your job is to, and it's a very straightforward exercise here, so nothing surprising, just want to give you the experience of doing it at least once. Correct this file so that it actually wraps the function we just saw inside of our Levenshtein.c file. And if you look at Levenshtein.h, here's the interface that we're wrapping. Okay, so there's nothing surprising here, nothing fancy. And then there's a setup.py, and the one we care about is the Levenstein-CYTHON extension. So when we're wrapping stuff, we need to use extension objects because we need to tell distutils that not only are we compiling this PYX file for the CYTHON wrapper part, but we're also going to be compiling the C file for the actual guts of the thing we're wrapping. So that's why we're using extension objects, which gives us the ability to say, here's the name of the results, and here are the sources that you need to compile together to give us our working extension module. So we have one for our just working example, and then we have one for the solution here. Okay. And then, yes?
So both those steps were still happening when we were using CypherNights, right?
Yes, that's right. So yeah, the question is, both of those steps were still happening when we were using CypherNights. That's right. The reason we're using this interface is because we need to give distutils more information to tell it not just to compile just the PYX file, but also to compile that with the C source code. And we're still using Cythonize here, but we're passing in our extension objects as arguments now. And so Cythonize will first run Cython on all the PYX files, and then it will hand everything off to distutils to compile all the sources together into our extension modules for us. Okay. So if we run things at Python, setup.py, build x-if, it's going to be a lot of compilation now. There's going to be, compiling POX files into C files, compiling all the C files into object files, and then compiling all the object files, linking them together into shared object extension modules. So if that's successful, you should see Levenstein-CYTHON.so and Levenstein-Solution.so. And again, right now the Levenstein-CYTHON doesn't do anything. If we look at our test thing here, we've commented out the time it stuff for the CYTHON version, just because it's stubbed out, it won't work at this point, but we do have it for the solution at least. And runs pretty fast. We'd expect it to do so, given that this is all at the C level. And you're running it for 200,000 times. This is much, much faster than the recursive version we saw before. We had to really crank down the number of iterations to get that to run in a reasonable amount of time. So anyway, that's the setup. I'll leave it to you to actually implement that Levenstein-CYTHON.pyx file to properly wrap things. And then we'll break for now. 15 minutes, so we're going to start up again at 10:20. And I believe there's snacks and refreshments, or just breakfast, food, and that sort of thing is still out in the main area here.
One is coming because you have one sign.
Okay, we'll start in just a minute here. Yeah, there are a number of them, actually, pretty big libraries too. The, so the, the biggest one that comes to mind is it's MPI for Pi.
So that's strictly C, C++, and then you just kind of expose the interface to Python?
That's right. It's a, I believe it's a C only API. Excuse me. But yeah, it's a Cython project to wrap the MPI standard interface. What's that? Oh, thank you. Yes, H5Pi is another one I should have on here. So wrapping the HDF5 API.
Are they basically gaining two separate code bases in order to support that since there is no automatic wrapping?
Yes. Yeah, they have their Cython wrappers. They have this. There's a C code base which is just part of the library that they distribute, and then they have the Cython wrappers for them, right? One reason, so Lissandro Dassine is the developer on the MPI for Pi project. I forget the name of the main guy on H5. Thank you, Andrew Collette. Oh, he is, okay. Great, thank you. One reason that Lissandro used Cython for MPI for Pi, people ask him about this, is because it gives him much more control over the Python interface. It lets him, for instance, if you were to wrap it with Swig, for example, right? You could get something that it works and wraps the whole thing and gives you something that you can call from Python very quickly. But the issue is that the interface is very C++ or C-like, or C++-like if you're wrapping C++ interface that way. And so all your time is then spent going in and tweaking the Swig wrappers to convert, to put in type maps and that kind of thing, to convert from the right Python type to the right C type or that sort of thing. And if you have a nice C library that's already kind of works with simple Python types and you can get away with it and not have to do too much work there. But if you have something that's really array heavy or really doing stuff where you want to have really high level, nice, very high performance wrappers, then you're going to be spending a lot of time tweaking that interface. And if you have to do a lot of tweaking in Swig, it's very painful. And so Lissandro said, and he claimed that he was able to wrap MPI for Pi in the way he wanted to, as efficiently as if he were to use Swig, because he would have had to tweak the Swig wrappers so much anyway. And he has so much more control with Cython, and since Cython is a full-fledged language rather than a DSL for wrapping, you have much more at your command to be able to use because of that. So he wanted the flexibility and the power that Cython brings specifically to wrap MPI for Pi. And in my mind, he did a really nice job. Like the interface he gave is really nice. H5 Pi is also really nice.
I'm curious how much time developers spend developing their C++ code versus get C++ working, and that's great. Now,
Sure.
that interface, how much extra time I have to spend?
Yeah. So at least for these examples I'm giving here, the C++ or C code is external to them, and they're just wrapping a standard API, right? So some other group, some other people just wrote the C or C++ code, right? And now someone comes along and says, I want nice Python wrappers for these. My job is just that Python wrapper part, right?
So you're not doing both.
You're not doing both necessarily. So there are definitely trade-offs here. And some people really like Boost Python because, Boost has a lot of really high-level cool stuff it uses for automatically inspecting the signatures of C++ functions and generating a Python interface for them. Some people really, really like that. You still have to go through and declare something for each function, but there are also projects, I'm not sure how mature they are, but that can generate Boost Python wrappers for you. So if you like to go down the Boost route, and Boost Python is there, that gives you a lot of power. But again, you still have to do some work, and depending on how much of a gap there is between the Python interface you want and the C++ code, then there has to be something that fills in that gap to convert types one to the other and perhaps do things in a certain way so you don't copy unnecessarily, that sort of thing. So And there's no substitute for that. Like if your C++ types just don't match your Python types well at all, something has to convert the types somehow. And so you have to figure out how that's going to happen, whether it's in Python or Swig type maps or other wrapper projects that allow you to do that sort of thing. So, and again, if you're doing that a lot, then the argument that at least Lissandro and others have made is that you might as well be using Python because it's a full-fledged language. It gives you all this really powerful stuff, and it's very Python-like, so it's very familiar from that point of view, rather than using these other things that can be a little bit harder to do that in. So a lot of trade-offs. No solid answer. Yeah, Swig is amazing in what it can do. In large part because it has a C++ parser as part of it. That's the big win with Swig. And it's taken decades to get there, to do that robustly and that sort of thing. But I've also used Swig in a fairly large project. And yeah, to get it working, to slurp in everything and just get something that will be able to be called from Python, very, very quick. But to take it to the next level, to really make it work with NumPy arrays in a nice way without copying necessarily, that kind of thing, then you really start digging in and dealing with all the inconsistencies that Swig has. So, not to rag on Swig, it's a fantastic project. It's just,
Yeah, I'm definitely in a dilemma of what to choose.
Uh-huh.
So, I'm ready to be sold on Python.
And so I would definitely look at cross-stress or X-stress. That's definitely something you should look at least, because it will automatically generate Python wrappers for you, kind of filling that niche.
It looks like, I just tried visiting the website, it's down, and the mailing list looks like it, Andy doesn't have time to.
I've not been up to date on it recently, so I'm not sure. I know he's been soliciting people to kind of offload the work to others. Mm-hmm. Any other questions? Yes? How does Python compare to Numba? It's a really good question. I'll touch on that towards the end of in our summary. And other JIT compilers and that sort of thing as well. Yes?
So if you're on Mac and you have GCC and you have Clang installed, how is Python selling looking at CC?
Good question. So the question is if you have multiple compilers installed, for instance, if you have GCC and Clang available, how does Python you know which one to use, or how can you control that? So your Python executable was built with a particular compiler, or it knows it has configuration options that indicate what compiler and what flags should be used to compile extension modules for that Python interpreter. And so if things work correctly, and they don't always work correctly, but if they work correctly, then Python will find that compiler with those flags and use that for compiling other extension modules, so everything's consistent, in theory. Sometimes it doesn't quite always work. You can control that with environment variables. You can set the CC environment variable to and distutils and set up that POI script that will respect that and use that compiler instead. You can use the C flags, environment variable, that sort of thing, to tweak options in the compiler and that sort of thing. So are you having issues compiling, or no? Just curious. Okay. Really good question. So what about on Windows when CPython's compiled with Visual Studio? So the Windows story is, when you're talking about this sort of thing, is always more complicated. You can look on the Python wiki. The Python GitHub page has a wiki that has a whole breakdown of the latest recommendations for what to use for compiling Python. I would be using that here, except it's fairly involved and there's a lot of overhead. Just getting it set up. I wanted the quick and dirty solution just so people could try stuff out. But that's kind of the standard reference for what to use. Microsoft's been getting much better about providing something for people to be able to compile extension modules for Python on Windows in a robust way that will work with Python. And there are a number of options out there now. I think this is kind of always going to be an evolving thing. There's the latest, as I understand it, there's like an SDK you can download and use, which has all just the pieces you need to link against and like a minimal component of the Visual Studio compiler to use to compile for Python extensions. I think there's at least one other option there, but we're doing the quick and dirty thing and using MinGW here, which will work for the examples I've tested, but may not work all the time for like things like printing and other kind of edge cases. Yes.
Very quickly, how does distribution work with Python build?
Good question. So I'm going to touch on that. I also want to touch on Python 3. So the question is on distribution. How does distribution work? And let me, previous slide as well. So here we have our PYX file, right? And then you run the Python compiler on it, whether something runs that for you or you run it explicitly. And that spits out a fib.c file, just a standard C file here. And then the next step is to take that and compile it to a extension module for your platform. The Python is intended to work so that you can develop this PYX file yourself, and then you generate the C file, and then you distribute the C file to people. And they, if you do pip install NumPy or pip install pandas, for example, it goes and finds the pandas package from PyPI, brings it down, and if you look inside, there's just a bunch of C files that Wes, or I guess whoever is maintaining or working on pandas now has just generated statically before they bundled everything and uploaded it to PyPI. It's just the C files that are distributed. So the end user doesn't even have to have the Python package anymore. It's all completely independent of Python now. And you just describe your C files to distutils, and it will go in, or setup tools, and it will go in and compile things for your platform and give you a working package. And so the nice thing is that once Python has generated the C file, you don't need Python anymore. It's done. So it's very easy in terms of just getting it to people using just Python standard compilation and distutils capabilities to compile extension modules for you. Yeah, it's just a matter of then kind of describing your package, saying this C file that I'm going to generate lives here, and this is the extension module that I want you to create from it, and then you can just bundle it all up and upload it.
So any users need to have the development tool?
Yeah, so you can also go down the wheel route as well, where you have binary bundles as well, and then they don't even need a compiler anymore, right? They just download and use the binary extension module. So you can take it even further and remove the compilation step. That's correct. So yeah, that pushes the effort to you then to have the platforms to compile for, to make sure you're compiling for all those and uploading the right wheels and that sort of thing. Yes?
For that, you only need 3, you only need Mac, Windows, and Linux.
Yeah, that would cover the vast majority of cases, but you also would, if you care about it, you need to worry about architecture as well, 32 or 64-bit, making sure you're compiling consistently for those, cross-compiling for those different architectures. So. Okay, I wanted to touch also on Python 3, which has come up a couple times now. So the wonderful thing about Python is no matter what code it compiles, it always generates C code that is, at the C level, compatible with both Python 2 and Python 3. It's up to you to determine how you compile it and what mode. You can also tell Python, assume only Python 3 semantics or assume only Python 2 semantics when you're compiling stuff. But if you don't tell it, it will generate code that can work on either Python 2 or Python 3. So it's the effort is in the compilation step to make sure you're compiling things correctly. You would want to make sure you're using a Python 3 interpreter and that sort of thing. But the nice thing is that Python it has lots of things to make sure it's generating code that can be either Python 2 or Python 3 compatible. This definitely comes up with strings and Unicode objects and bytes and that sort of thing. I don't have time to get into it. There's lots of documentation online and other places where you can use things known as Python directives that allow you to either have decorators that Python understands, or file level comments, special comments that Python will use to kind of control how Python interprets things inside of that file, or you can use even compiler flags, like when you say Python, you can say -x and give a directive to control some aspect of its compilation. And this allows you to go in and say, whenever you see a string, just a literal string, treat it as a Python 3 Unicode object, or treat it as a Python 2 string object, or that sort of thing. So you can go in there and control exactly. Or you can say, use this default encoding whenever you see a literal string so that it can be a valid Unicode string in Python 3, that sort of thing. So you have several directives related to string manipulation, different string types, to control how Python treats strings and works with strings and string data. Of course, to be safe, you can use like the bytes type, which is Python 2 and Python 3 compatible. It's unambiguous when you create a bytes object or have a string prefix with a lowercase b, right? That makes it a literal byte string. Then you know exactly what you're dealing with there. You can do the same thing with Unicode. You can make explicit Unicode objects, or you can prefix a literal string with lowercase u, or I guess uppercase as well. But to make it a explicit Unicode string, so those work fine in Python, and you're being very clear and explicit about exactly what you're using there. It's just in the ambiguous middle grounds, when you have a literal string that doesn't have any prefix on it, that's when you can control how Python treats those things and what it does by default. So again, just to show you, if you just say Python -h, this last argument here, -x or -- directive, this is where you can say the directive name and the value, and that allows you to control things. There's a -2 and a -3 argument that allows you to tell Python, assume Python 3 or Python 2 semantics only. Yes?
If you pick one of those options, do you get a performance boost, or is it just
It's more to resolve type ambiguities and to resolve ambiguities that might arise in Python 2 versus Python 3. For instance, if you use a print function without saying from future import print function, right? If you're compiling in Python 2 mode, that's an error, right? Because print is a statement, not a function, right? If you use it in Python 3 mode, print is a function by default, so that will just work. So it's more just for the cases that are different between Python 2 and Python 3. The performance aspect, there may be, I'm not certain what that would be. Let's see, there's one more thing I wanted to. Several options here, I can't recall. So there is a little bit of work for compiling code in Python 2 and Python 3 with Python. The nice thing though is that Python will generate code that is, Python 2 and Python 3 compatible. And anyone who's ever written extension modules by hand knows that this is where the Python 2, Python 3 divide really hurts. Because like writing code at the C level using the Python C API, there are many more changes at the C level between Python 2 and Python 3 than at the Python level. And Python takes care of all that for us. So there's a big plus there in terms of the code that Python generates. So questions on Python 2, Python 3? Okay. Other questions in general? All right, let's continue. We stopped at that exercise. Let's just touch on it quickly. There's one little thing I wanted to point out. So we have Levenstein-Cython, PYX. Here I'm going to uncomment this stuff, get rid of that line, and get the header file. So some people just tried to grab the declaration, indent it, and you will need to get rid of that semicolon. And then we can just now try to call this and say return Levenstein dist s and t. And let's try this. So that worked for me. Some people had issues with consts. Oh, okay. Oh, wait. Yeah, I gotta add the. So this may be something that they improved in the latest version of Python. Do you know what version you're using? Interesting. Interesting. So you got a runtime exception relating to const somehow. Okay. Was it an actual exception? Was it like a? Interesting. Okay. I'm on 2. You're on 2 as well. Okay. If you don't mind, and if you're willing to, I'd like to just take a look and see afterwards to see what's going on. Because I specifically added the const here just so people could at least wonder what's going on with the const. Python, PYX. So it used to be that Python didn't even have support the const keyword, didn't really know about it, didn't care. And most cases it didn't matter, because, again, the important thing is that you could get rid of these consts and it wouldn't affect anything at all, because the const is just really for C's sake, to tell C, the C compiler, when you're compiling this code, make sure no one ever modifies the C arrays, the C strings that you're passing in. From Python's purposes, you can call that thing, and as long as you're passing in a C string, it doesn't matter from Python's end. And again, Python just generates an include statement from this. It never redeclares this function at the C level. So it doesn't matter that there's a slight inconsistency between the Python declaration here and the actual C declaration. It won't be an issue. We can, of course, well, at least I was able to keep the const in there, and that wasn't an issue.
So I don't have const, but I am getting runtime errors sometimes. Like I'll run it randomly, sometimes it will give runtime errors.
So your Windows, right? Your Linux? Okay. This could very well be, I would almost certainly put this on a mistake I made in the actual implementation somewhere, or some other thing that I put in, because I would expect this to be bulletproof from the Python part of things. So
I'm also getting similar randomly.
Linux. Okay. And you're on Linux as well. Okay. Yes. Oh, negative number for the final answer. I see. So you will notice that, let's see. Yeah, this is almost certainly a mistake I made implementing this. What's that? Yeah, it could yeah, that's right. We're dealing with C code, right? I made a mistake almost certainly. There's almost certainly something I'm doing wrong in the implementation. I threw this together faster than I should have last night. Didn't have time to test it, so this is on me. I apologize. It's interesting that it's just Linux. Yes.
So you shouldn't have to do anything like cast the SMT in the def function you've got there and the char star.
No. Nope, because the string types are compatible with char stars. If you try to pass in an incompatible type, if integers, for example, it won't work. So, there will be a Python exception before you even call that. Python will generate that for us. So again, the error, I apologize. I should have tested this more on more platforms, but it's almost certainly a mistake I made in the implementation somewhere. So I'll look into that a little bit more. And it's interesting that it's only on Linux. Yes. A CPP. Oh, cpdef for. Oh, to this external function? It'd be nice, it'd be really nice if you could. It's just that Python doesn't implement it that way. There's declaration part here, and then the implementation is something separate. It would be nice if you just declare something cpdef and then have Python generate a nice Python wrapper around it and that sort of thing. That would really, there's no ambiguity about what's going on there. It's just, it doesn't. But this does give us the ability to, if we look at the solution file, so I didn't really do it right here because there is an error code that's returned. And there's no way you could have known this. It's more me just not giving good instructions. But if Levenshtein distance returns -1 or something less than 0, that's an error state. This is a C interface. We have to check for error codes and make sure we do the right thing. So that's why some people are getting a runtime error, because for some reason there's,
I think it's definitely a memory issue of some sort. I think in Linux it's not clean enough that it's probably accessing a memory out of balance.
yeah. No, it doesn't. Yeah, there's definitely, you're right. There's definitely some initialization issue going on here. If you zero it, it works. Okay, thank you. So again, I'm not surprised. I thought I had it. It tested and worked fine on Mac, but again, I didn't test it sufficiently. So, but there is this error state that, if for instance, well, the idea is if this runs properly, it should only ever return a 0 or positive number, right? If it turns negative, we can use that to detect an error state, which is what we're trying to do here. Every now and then, because there's some initialization error, it returns negative. Anyway, we detect that, and we can then know, again, if this were implemented correctly, we would know that there's some error, so we can raise a Python runtime error in that case, okay? Which is what we're doing here. And I will correct this and put the updated correct version online so people can use that for reference later. Yeah, again, so we're using a C interface. There's no exceptions in C, so we have to detect error codes and raise the appropriate Python exception in those cases, which is what we're trying to do here. We want to be very explicit and make sure we do that. And we have to do that explicitly for C APIs. For C++, C++ has exceptions. Python can generate code that captures C++ exceptions and converts them into appropriate Python exceptions. And we have the ability to control that a little bit as well. Again, a little bit out of scope for this tutorial, so leave that to you to look into on your own if you are wrapping and working with C++ APIs. We'll try to touch on C++ a little bit later on, though, in some of the extra material. So again, apologies, I messed up, but I'll fix it and get the right version uploaded for your reference later. Hopefully the goal of the exercise wasn't lost in you. All right, let's continue. Now getting into Python and NumPy. So a lot of people who have worked on Python are kind of in the scientific Python world because they wanted a Python compiler, basically. And Python's been around for a long time now. It was there long before, any of these JITs were out and kind of up and running, way before PyPy was ever ready for real-world use, way before Numba, that sort of thing. You may have heard of Pyrex, which is Python's predecessor. It's the reason why Python has a PYX extension. This is a holdover from Pyrex. Python is a fork of Pyrex, so it's a very friendly fork. Greg Ewing is very nice and kind of, there's a lot of cross-pollination between the two projects. I believe, though, Python is much more heavily used than Pyrex. Pyrex is kind of lapsed for a while now. But this here, what we're going to be talking about, Python's NumPy support, is one of the areas where Python has really taken things very far. Because again, a lot of the people using Python and working with Python wanted to use Python to improve their numeric code. And the kind of standard way, the best way to use and interact with arrays and memory buffers and that sort of thing from Python are these things called typed memory views. And they're a Python level construct. They're something that only exists in Python. They're meant to be familiar to people who know NumPy, and they're meant to be similar to the memory view object in Python, or the memview object in Python, if you've ever worked with those before. But they're this Python-specific thing with its own syntax, although it's very NumPy-like, that's meant to be interoperable with NumPy arrays and C arrays and C++ standard vectors and array-data arrays and that kind of thing. So they kind of allow you to talk about and represent buffers, memory buffers, in a consistent way at the Python level and in a very efficient way. So here we have a stack diagram kind of saying we have Python memory views and NumPy arrays at the top, kind of at the Python layer. We have this middle Python layer, which kind of allows us to work with all these things. And then below that, we have C arrays, standard vectors, that sort of thing. The syntax for declaring type memory views is suggestive. I mean, it's indicating the type, the D type for the elements, so kind of like a NumPy concept of a D type, and then the dimensionality and how and if and how this memory view is meant to be, its continuity, basically. So for instance, here, we're declaring A, the argument, to be a typed memory view. The underlying D type is double, and its dimensionality is one-dimensional, and this : 1 here, this funny-looking thing, is meant to suggest that it's contiguous. So if you think about it, in slicing syntax, the : the last slot, the optional last slot, is meant to indicate the step. Well, the step is 1, then the elements are right next to each other. So that's the typed memory view way of saying that this thing is contiguous in memory because the step in this dimension is 1. They're all right next to each other. And this comes up as well when we have multidimensional memory views, which you'll see in a little bit. And so we have this thing A now. It's this typed memory view. And inside of this function, we declare a double S, some integers, and then we loop through for I in range n. And we just say A plus equals A of I. Right? So we're indexing into it as if it were a list or a NumPy array. And we're just adding up the elements, so nothing surprising here. And we can use it just like NumPy arrays. So if we have a 1,000,000 element NumPy array, A, if we see how long the built-in, let's see, so this is our sum here, and that takes about a microsecond to run. And the built-in NumPy sum also takes about a millisecond. And if you were to write this just in straight C, you would find that for the C guts part of it, not the converting from Python to C parts, that also takes on the order of a millisecond. So we're getting, I'm kind of just declaring without proving, but trust me here, that we're getting C-level performance out of these type memory views. So when we're accessing these things, that sort of thing, if you look at the generated code, it looks pretty ugly, but it's actually resolving to fairly straightforward just accessing elements inside of a buffer of data. Okay? So that's the goal here. It's to give us this kind of high-level syntax for declaring these array-like objects, these type memory views, and being able to interact with them as if they were like NumPy arrays. And but still get C-level performance when we're indexing into them, doing operations with them, that sort of thing. So a little bit more details. So here we're declaring a type memory view in Python called MV. And here its D type is int, and it's 3-dimensional. So : : So it's a 3-dimensional type memory view. Here we're also declaring an array, but it's a regular plain old C array, stack allocated C array. Okay? So int A 333, right? So 27 element memory view. So we can, what we can do is we can assign, I don't have it here, unfortunately, I apologize, but if you just say MV equals A, right, after declaring these things, that's perfectly valid operation. And what that does is now we have this memory view thing, this NumPy-like thing. It's referring to the data that was allocated in this C array, this three-dimensional C array. Okay. And that will work just fine. So now we have this memory view that's being backed by, that's viewing data that was inside of a C array. Okay. So that, again, and I apologize I don't have it here, but if I had said MV equals A, that's when the memory view is acquiring the data inside of the C array, A here. You can also just declare a NumPy array. Here we have a 10 by 20 by 30 NumPy array, A. We can also say MV equals A here, right? And so now the type memory view is reaching in and grabbing the underlying buffer inside of that NumPy array and using that for its operations. Okay. And we can also use a memory view that looks at another memory view. Okay, so you can have multiple memory views referring to the same thing ultimately. Okay, so this idea of views in NumPy, kind of take that concept and think about it in terms of these memory view objects in Python. They're viewing some buffer of data that is either allocated at C or in NumPy or that sort of thing. Question?
So NumPy arrays are guaranteed to be contiguous?
Not always, no.
So you have to be careful if you're, so I mean, I'm sort of thinking you could pass a NumPy array with one of its functions and declare it as a contiguous array, but you have to be careful because it's not always contiguous. NumPy arrays are guaranteed.
Yes, so it's a very good question. So just general question about continuity and these memory views and that sort of thing. So when we declare a memory view like this, just with colons, we didn't specify, back here, when we just said : 1 for this one-dimensional memory view, that's saying this memory view can only acquire a view on something if that thing is contiguous. It will raise an exception at runtime if you try to use this with a non-contiguous NumPy array, for example. Okay. So this says I only want to use this on contiguous things. If you try to use a non-contiguous thing with this, you'll get an exception. Okay. Here, we didn't specify : 1 anywhere. Right? We didn't say this dimension has to be contiguous. So this is more general. This memory view can work with non-contiguous data. So for instance, you can use it with a NumPy array that's been sliced, for example. So a non-contiguous view, another array. As long as it's three-dimensional and of integer D type, that will work with this memory view here. So memory views can, again, just to emphasize, they can work with C arrays, they can work with NumPy arrays, they can work with other memory views. They can also be maybe work with C++, buffers of data, that sort of thing. So they're very flexible. They allow us to kind of group together a whole host of ways of working with buffers of data at the C level and represent them as these nice things at the Python level. You can index into them, kind of just like NumPy arrays, nothing surprising there. You can also slice them. So you can, use partial indexing to kind of implicitly slice them. You can explicitly slice them with colons. You can use ellipses to slice them, that sort of thing. And a slice of a memory view will generate another memory view. So both memory views, just like NumPy, are referring to the same underlying data. So they're very, very efficient in that sense that they aren't copying data around. So you can use ellipses inside of brackets to say basically, so you don't even know how many dimensions you have in an array, right? The ellipses will just fill in colons to give you a slice of that size. You could have 10 comma ellipses comma 10, and it will just fill in colons for the number of dimensions to be valid. So we can do a lot with memory views, and this is talking about being able to have very general memory views that can work with non-contiguous data, or we can say we want a memory view to be specifically C-contiguous or Fortran contiguous in different situations. So here we have a memory view that's again, a three-dimensional memory view, strided MV. We didn't do anything special with the declaration here. They're just straight colons. So that means this memory view can be used to acquire data that is not contiguous. So for instance, if we have a NumPy array here, it's not contiguous in these dimensions at all. So, but we can use that memory view to acquire a view onto the data in this strided array. That's not a problem. Now, if we want to make sure that we have a multidimensional memory view that can only be used with C-contiguous data, then we use colon, say we want it to be three-dimensional. We would say int : : 1. And again, C-contiguous, its last dimension varies fastest, right? That's the contiguous dimension for C layout. So here we're saying the last dimension here needs to have a stride of 1. So this is a C-contiguous memory view, and we can use that to interact with a just default NumPy array. And since by default NumPy arrays are C-contiguous, when you create them anew, this will work. But if we try to do this on a non-contiguous NumPy array, we get a value error at runtime. Now, we can also put a : 1 in the first slot to make it Fortran contiguous, so as if the first dimension is varying the fastest. And then we can use this memory view, fcontig, on a Fortran, so np.as Fortran array, to make a Fortran contiguous version of the array. All right, so we have a little exercise here now on working with arrays in Python. So 04 arrays is where we are. Now, I tested this one a bit more, so
You have the same bug in C file, so you'll have the same issue.
well, not necessarily. If people get a bug, let me know, and I'll fix it. Did you try it already? Dang it. I was hoping,
You just have to do a mix set.
yeah, you're right,
Below your mallet, that's all.
you're right. If I change the limit to start at 0 instead of 1. Okay. I see. Thank you. Right, right. Yeah, that would definitely throw things off. So, so you're saying here in this file, C file, okay. But we're in the arrays exercise now, right? So, there isn't a C file here. Curious if I can get it to barf. Let's try this a few times. So this exercise is we have the same setup as before. We have a pure Python version of this thing. Let me send that pi. This is just using NumPy to use the array version of our Levenshtein distance. It's kind of using dynamic programming to just initialize an array, the edges, and then just fill in the values using the right calculation to figure out where the substitutions are, where the deletions are, where the matching characters are, and then just update the distance between these two strings are, depending on the prefix length that we're looking at. So the implementation is not important for this, really. It's just really looking at the types and that sort of thing. Well, it's important in the sense that I had a bug before, but not important in the sense of I don't want you to pay attention to the implementation too much. But if you look here, we have some simple types here, right? M and N are both integers. D is a NumPy array. And then we initialize the rows of D to certain values and the columns of D to certain values. The leading rows and the leading columns. And then we're just going to be looping through the remaining values and then kind of propagating this distance calculation according to this if-else block here. Okay. So I'm a little skittish given the error before, but I'm pretty confident that since, first of all, since this is zeros here, and by inspection, I'm pretty sure these are doing the right thing as well. I think this is doing the right thing. Anyway, so this is the pure Python version. It's nested for loops. There's a good amount of logic within the for loop, so we know from experience to expect this to be pretty slow in Python. Right? Especially if these strings get long, our array gets much bigger, right? It's going to be the length, the product of the lengths is going to be the size of this array, so it can get fairly large pretty quick, so there's a lot of operations going on here. It's still going to be more efficient than the recursive version before because we're not recomputing stuff unnecessarily, but there's still a lot of room for improvement here. So this is the pure Python version, and there's TO.PYTHON.CYTHON, excuse me. And really, again, we just copied, I'm going to get rid of that comment at the top there. Just copied over our Python and gave it a different extension, basically. Okay, so same operations, get rid of that at the bottom as well. Still using NumPy, that sort of thing, just a regular def function. We didn't add any static typing at all. But when we run this, we get a little bit of a boost. So 3.77 to 3.41, so like 10%-ish performance boost. But now you see the optimized version is like 100 times faster or more than the Python or the CyThon version. So there's a big gap between what we have right now and where we can get to with using a little bit of CyThon. So your job is to look at that Levenstein-CyThon.pyx, think about what you can add to add type information to speed this up. Every time you make a modification, you need to make sure you recompile. If you're on Mac or Linux, you can just type make. We'll recompile everything and then run the timing script to see what the output is again and see what sort of changes, if any, your typing makes to the performance. We're working with NumPy arrays now, right? So there's this array aspect to it. And this is where we start thinking about, okay, how can we use type memory views here? And it's very simple, the way we would declare and use them from Python code. It's very easy since type memory views obviously support indexing, and they obviously also can work with NumPy arrays. You can assign them to NumPy arrays. So from that point of view, there's not much you have to do other than just declare this thing as a type memory view in Python. That's really kind of your role here, as well as declaring the other scalars to be static C types as well, so that Python can generate faster code.
If you do cpdef or cdef on your function
Yeah, so the comment was if you use cpdef or cdef on functions, then the tracebacks, if there are exceptions or errors, get a lot harder to read, harder to work with, in part because there's name mangling involved now, and there's maybe other function calls going on, so it's harder to trace where you were and that sort of thing. So that's definitely a good point. Another goal of these exercises is just get used to the edit, compile, run step process that you often go through with Python if you're using a distutils script like this. Of course, we saw pix import before. We could get things set up there so that you just allows you to just import your PYX files directly from Python, which is nice. I didn't set things up that way just because, again, when you're doing Python for real, more than just exploratory or just trying something quick, people tend to just go the whole way and just have a setup.py script and use that, just because they're going to be distributing it with that setup.py script anyway. So, and again, it gives us the ability to go in and have more control over many aspects of the compilation if we need to. So the question is if you have a large C++ library but you only care about interfacing with one or just a few, but that depends on a lot of your whole project, that sort of thing. As far as Python is concerned, it only needs to see the interface of the few things you want to interface with. You don't need to declare everything. So if you just want one function to call from Python, you can just declare that. But it's more a matter of the compilation part. You need to make sure you're compiling all the C files or C++ files that you need. Correct. Yeah, you would need to list all of them. And I should mention too that you can get Python to integrate with other build systems. So for instance, if you have CMake, you can get Python to work with that. You can get to work with just regular GNU Make or scons or any of those. They have ability to either already use Python or you can just define a rule to say, if you see a PYX file, generate a C file from it or CPP file, and then compile extension module for that. So, yes. If you use mp.ndarray, can you point to, like in here, you're saying, in this? So you're saying, you're saying declared as a, I see. And I guess int here, yeah. So the old way. But you're saying this is how much faster are you noticing? Very small. Okay. I would hope so. But yeah, there is an old way of working with NumPy arrays, and it uses this syntax. You would say something like, you'll often see it as like cdef mp.ndarray, where you first C import NumPy as MP at the top here. So we can talk about C imports. I might touch on that a little bit later here. But, and you can say, R equals mp dot something. Right. You might see this. This is still around. This is still supported by Python. This is kind of the old way of interacting with NumPy arrays. The type memory view stuff that I'm presenting here is meant to replace that. It's more general, and there are situations where the type memory views are faster than this. I wouldn't expect there to be any dramatic difference, and since this isn't supported anymore, it'll still be around so that people's code won't break, but it's not actively developed. So that the typed, they'll fix bugs if there are bugs or that sort of thing. But if the type memory view stuff will get faster and faster as time goes on. Yeah, yes you can. You would have to, just make sure that the C type that you're using here is, Cython knows about it. So if it's a built-in C type, then you can just use it straight out. You may have to tell Cython where the type lives or where it's defined, or if it's a type def or that sort of thing, you may have to declare that type to Cython so it can use it in this slot. But you can absolutely, whatever C type Cython knows about, you can stick in that slot there, or you can stick it in the front of our type memory view part here to tell it the D type to use internally. Okay, so I'm just kind of skipping ahead here, going to the solution file. I wanted to point out a couple things that again, are a bit outside the scope of this exercise, but just so you're aware of. So that, I'll talk about these decorators here in a little bit, but ignore them for now. So here's our Levenstein distance. I declared the argument types as two C strings, S and T. And then we're declaring a bunch of integer types here, I and J, M and N. M and N are just the lengths of our strings. And here's where really the core of our, like the work of the exercise is. We're declaring a type memory view, integer D type, two-dimensional, and the : 1 in the second slot is saying this is a C contiguous type memory view. So it can only be used with C contiguous data. Okay? And that's trading off flexibility for performance. If we instead just said int : here, that would be a strided memory view, so it can be used with things that aren't C contiguous. Yes? Correct. It'll work either way. This version here that I just put in, it's more flexible. It can work with anything, even strided data. But since we know that this is an internal array anyway, we have control over how it's created, so we know there's never going to be an issue with it being C contiguous. So we just declare it C contiguous by default. This just allows Cython to generate faster code inside of the loops when it's indexing into this thing. So that's all the declarations. And I guess, let's see. So thinking back, I realized that the original version used slicing and slice assignment for initializing things. The type memory views, you can slice them to get a memory view back, but you can't use slice assignment with them. There's something a little wonky with it. There's no reason why it shouldn't. It's just a matter of someone implementing it. So here we have to use for loops to initialize the edges. So I apologize, that may not have been clear. You probably got issues out of the box, so that one's on me. I should have made it work out of the box here with these for loops. But yes.
What I did was to declare the NumPy array initially with different variable name and set it to the type memory E.
Mm-hmm.
Then these slice assignments work just fine.
Interesting. Slice assignment on the NumPy array?
NumPy array.
Oh yeah, that'll work. That'll work just fine actually. So yeah, if we declared a NumPy array, so R equals, it's actually, so here's our NumPy array, right? And then we can just say D equals R, for example. Oh, it's not going to work. Let's do this. So here I just have a naked type memory view D, right? I declare my NumPy array R, it's untyped. So Cython just treats this as a general Python object. And then we can use D equals A, our R here, right? So this here is, the memory view D is acquiring a view on our NumPy array R. But we can interact with this same data, right? Whether it's through the NumPy array or through the memory view. So it's a very good point. You can now just use your array here to use slice assignment with NumPy arrays to have all the even higher level NumPy stuff. We're still just modifying the same underlying data, right? So yeah, that's.
The opposite, can you grab like a basic raw Python object from the memory view?
So you can return memory views from functions to Python, and they'll be represented as just regular mem views at the Python level, which can be trivially converted into NumPy arrays. Or you could say, if you have a memory view, you could say, for instance, like return mp.ndarray, or you could do this, for example, mp.asArrayD. You could return that thing. That will give you back a NumPy array that's obviously like getting its contents from this memory view without copying. So it's very efficient, it's very quick to return NumPy arrays using memory views this way. So that's probably the most common way of doing it. So just to show you the original version here. So here we're initializing the rows. Here we're initializing the columns. Okay. Then we have our loop. And all this is the same. Okay. The nested for loops is identical. And if you look here, we're just interacting with D as if it were just a regular array, right? Two-dimensional array. And change anything fundamentally, so we should get still the same performance as a result, but just wanted to walk through the solution file with you. What else to point out? These decorators. So again, this is just to lead you further beyond this tutorial, but there is this Cython import you can make inside of Cython code. Cython recognizes this as kind of like a magic module to allow you to control things. This is one way to control, this is one way to set these compiler directives, for example. You can use this Cython namespace and say Cython.boundCheck is false and Cython.wraparound is false. There are many other things that this special Cython module supports. And what we're doing here is, the name should be suggestive, we're turning off bounds checking, we're turning off wraparound checking inside of this function here. If you think about it, whenever you index into something in Python, Python is very safe, right? It will always do a bounds check whenever you index into something to make sure you're not outside of your array bounds. And you'll get a nice index error if you are, right? So it's very safe in that sense. That, of course, has overhead every single time you index into something. So it's a safety versus performance trade-off you're making there. There's also wraparound checking. You can index into things with negative indices in Python. Well, that's also a convenience, but there's logic in there to detect when you have a negative index and convert that to the appropriate positive index before it actually grabs some element of your array or list or whatever it is. So both of these things have overhead every single time you're indexing. Let's say we know ahead of time we are not using negative indexing anywhere inside of our function, and we know, because we've taken pains to make sure, that we're never indexing outside of the bounds of our array. If we know that, we can turn off those checks inside of the generated Cython code to, again, trade safety for performance. And the way you do that is with these two decorators, if you want to just turn it off just for a function body. There's also a context manager form of these. You can say with Cython.boundsCheck of false : and have an indented block, and inside of that context manager scope, bounds checking will be turned off. Same thing with wraparound checking, so you can make it even more limited in scope that way. You can make it file level scope, so everything inside of a single Python source file, you can turn off bounds checking and wraparound checking with a special comment. It looks like Python bounds check equals false, for instance. So Python looks for special comments right at the top of your file, and if they match a certain pattern, then it will apply that directive for the entire file for you. So there's kind of different levels at which you can specify these directives to control how the compiler works. Question? Yes?
Yeah, so just to be clear, if you violate these assumptions, bad things.
Yes. If you violate them, it's on you. It's definitely something you're taking responsibility for, which is also part. Yes, exactly. You'll get nasty, ugly sig faults and corrupted sig faults in the best case, corrupted data in the worst case, right? So it's definitely something you need to be careful of when you're doing this sort of thing. We know we can do it safely here because we have control over the array we're allocating. We have control over all the indices and that sort of thing. It's not like, and you can certainly do it with data that's coming in from the outside. You just have to make sure you're careful when you're doing this sort of thing. And another reason why Python provides kind of the file level, decorator function level, or context manager level is so you can be very specific about the scope for which this directive is applied. So you can be very limited in scope to say, I just want it to be applied in this just for a few lines, for example, inside of a function, which is nice, because then it's not like you're just saying, turn it off for the entire file, in which case it might be a little bit more than you're asking for. Yes, we'll talk about that in a little bit, yes. So a question about profiling, and we touched on that a little bit with the static profiling, the profiling directives. That's all I have for this talk, but there is also runtime profiling you can do with Python as well. And actually, the directive for that, it's file, I believe it's file only scope, you can do that, but you can say Python profile equals true. So when you put in that directive, for example, Python will instrument the generated code so that it can work with the C profile module. So now all the goodies that you have from C profiling, just say %run-p from IPython, Python will generate code that will work with that, and so you'll see entries for your Python functions in C profile. Let me just. I may not be able to do this at this time. Let's see. Let's try. This may not work because I'm handing off things to time it, which means the profiling might not be able to go inside and find it. There we go. So it is able to find it, which is great. So if that went too fast, let me just show you what I did. So inside of my Levenstein-Cython solution.poix, I put a single line at the top, Cython : profile equals true. And what that did is it now instrumented things so that our compiled Cython code can work with the C profile, just the standard Python profiling tools. Okay. So now at runtime, we can get feedback on how long our Cython code took to run. So now that I put that in, I recompile, so now Cython generates the right code for that, and now I can fire up IPython, and I can say like %run-p test Levenstein.py. It runs our code, but it also will bring up our profiling information afterwards. And I believe if I did this right, I'm pretty sure this wouldn't have shown up without it. But you notice here, we're seeing an entry for our Levenstein-Cython.Levenstein distance. So that's a compiled Cython function, but we're seeing it show up here inside of our profiling. And you can go further with this. You'll get more information about these calls, that sort of thing. So again, we have the static profiling that we get from kind of the compile time profiling from the Cython-A Levenstein-Cython solution. And that spits out a, interesting, that gives us our highlighted version of this. And if you look here, there's almost no yellow inside of the for loops down here, which is exactly what we're going for. It's also interesting to note that the min function is also not generating any Python code, so Cython's able to intelligently realize I'm calling min with some integer expressions here, so it's able to generate C code that doesn't involve any calls to the built-in min function, for example. So that's our static profiling information we can get, so it helps us find out which lines to focus on. And then we have our runtime profiling, which we get by using this profile directive inside of our code. And that then allows us to run our Cython code under the control of the Python profiling, and it will also hook into that for us. And there are some tutorials online as well for kind of a more complete example of using those two different kinds of profiling with Cython. So Cython's kind of tooling, it's profiling stuff, it's directives, that kind of thing, the ability to control how the compilation occurs, Python 2, Python 3 support, that sort of thing. Cython's been around for a while, so it's had the ability to implement a lot of these new features and kind of things that help you develop Cython code. So that's one of its strengths, is the maturity of the project and its ability to have these kind of tools that you can use. Any other questions? All right, let's continue then. So this is our kind of nominal wrap-up time, but we have a little bit of extra time, so I'll go into some extra topics after this. But some people mentioned how Cython compares to Numba, and there are other JIT compilers out there as well, SciPy and Piston's coming online. They're working on that at Dropbox and that sort of thing. So how does Cython compete in this age of JIT compilers, right? JIT compilers, of course, are compilers that just take plain Python code, and on the fly, when you're executing it, it will compile dynamically in some fashion to faster code and be running faster code for you under the hood. They take care of all those details. You don't have to even think about compilers as long as you're just running in the right environment with the right, decorators or imports or that sort of thing. So they're very convenient, very easy to use. Not nearly as cumbersome. Cython can feel cumbersome in comparison because you have this explicit compilation step and that sort of thing. So, and you can often get really nice performance out of these other JIT compilers as well. Some like Numba are targeted specifically for like array operations and that sort of thing. So they're very active, they're being developed heavily and that sort of thing. So how can Cython compete? Well, there are a few things. It's definitely, a valid question. There's definitely, it's a hard question for Cython to answer. But there are still some things that Cython gives us that JIT compilers don't or won't give us, just based on their fundamental design, right? JIT compilers are meant to work just with straight Python code. You might be able to tweak them in some fashion. I'm not familiar with all the options you have. But still, Cython, for the most part, I think I'm pretty confident in being able to make this statement that you are able to have much more control over the code that you're working with, you're generating with Cython. You have the full range of C types to use and work with. You have all Python to work with as well. So you can use any and all C constructs that you want, or C++ constructs for that matter, to lean on or pull on to help with your Cython, with the Cython code the code that Cython generates, I should say. So if you know you need exactly a certain type for an array or for a scalar, that sort of thing, for whatever reason, you can do that in Python. Or if you want to be able to use Python's profiling tools to help you figure out, these are the lines I need to add more type information to, and fill that out with more typing, you can do that with Python. Whereas JIT compilers are much more black box, they're more opaque. You can open them up a little bit. Some of them give you the ability to control the types, but in general, they don't give you nearly the level of control that Python gives you for these sorts of things. You can also, it's not fun, but we've seen the, well, it is easy, it is fun to look at the profiling output, the static profiling. You see the highlighting and see how your code is improving over time. You can even dig down, you can open up those lines and see what's inside there if you want to. It's not nice, Python mangles stuff a lot, but you get some idea about what's going on under the hood. Python has greater transparency in the sense that, again, these profiling tools that you can open up, you can see what's going on, and you also need to know more about what's going on under the hood a little bit to use that effectively, but at least you have the ability to kind of see what's going on. It's not just this black box that you're throwing Python code at, and if it gives you the speed up you want, that's great. If it doesn't, then you're kind of like, well, what exactly do I need to do to kind of shake, arrange my inputs in a certain way or my types in a certain fashion so that this JIT compiler can give me the code, the speed ups that I know I should be able to get out of it. Python, it's easier to kind of experiment and run experiments, have hypotheses about, well, maybe if I try this construct, or maybe if I get rid of this particular thing, it will speed up my code because then I can get rid of more Python. And again, we use things like the profiling, the annotation, and also the runtime profiling that we just saw to help give us information about how those experiments panned out. Python has very mature foreign function interface or wrapping capabilities that we saw as well. We can declare all sorts of stuff we didn't even touch on. Its ability to wrap C++, but we will get to that in a little bit here. And a lot of these JIT compilers don't even have that, or they're just starting to get that. Some I hear are getting better and better over time, like SciPy has CFFI, for example, for foreign function interface to C code, that sort of thing. It's a different way of doing it. I hear it's pretty nice. I haven't used it myself much, so I can't comment on it too much. But as I've mentioned, Python is used for wrapping massive libraries, HDF5, MPI for Pi, several others, because people like it for the control it gives them and for the ability to have very high level, but also very high performance wrappers around things. So Python, in terms of end user complexity, it can be easier because you've taken care of generating the C code and then the user just says pip install whatever. It's downloaded, compiled on the fly, and then installed. Or if you go through the steps of pre-compiling the binaries and uploading the wheels for those different platforms, then your end user doesn't have any complexity involved. Some JIT compilers can be, it can be a challenge to set up, of course. Like the times I have tried to use PyPy, it's been a while ago, so it was definitely a challenge. Python is meant to get out of your way. When it's done compiling stuff, you don't need Python anymore. You just use Python's built-in support for extension modules, and you're done. Okay? Now, of course, there is that compiler step that needs to occur, so there is complexity there, but that is still a fairly standard step for a lot of packages, so it kind of hooks into the standard steps that a lot of packages are already using. Python has a lot of mature diagnosis capabilities, so its maturity is one of its strong points, although that's eroding over time as these JIT compilers get more mature and probably will have more tooling associated with them. But at least for now, Python's tooling is definitely a strong point. And Python is good for both numerical and for general purpose Python. So it can speed up, it's not just meant for one part of your Python code, but it can also speed up general Python code that doesn't necessarily involve loops over arrays and that sort of thing, although that's one of its strong points, certainly. So I like Python because it's a fairly general purpose tool, but it does the many things it does them well. Right? It speeds up Python code well in a nice way, giving you the ability to just add C types intelligently. It also allows you to wrap foreign C or C++ code in Python in a fairly nice fashion. So if you know it well, you have the ability to kind of tackle almost any problem that involves Python and C or C++. You don't have to partition your knowledge into different areas just because you're doing one step versus another. So again, it's not necessarily a slam dunk at all. These JIT compilers are definitely getting better and better as time goes on. There may be scenarios where Python makes sense for just one part of what it does, and these JIT compilers get better and better and do it better than Python down the line. But at least for the foreseeable future, Python's going to be around for a long time. And as we saw, it's kind of at the foundational level of a lot of the packages we're already using. Any questions on, any comments? Yes?
I mean, so you showed us that you could take just a standard Python file and run it through Python and it will run. Are there limitations on that? Is it something not just to hit Python code?
Yeah, so the question is running Python on a .py file and other limitations with that and other things it can't support. I should mention that the Python code base itself, it's a Python code base, but when you install Python or Python, it self-compiles all those Python files into extension modules, and when you run the Python compiler, it's running that. So and Python codebase is huge, and it uses a lot of crazy stuff. So the fact that it's self-hosting in that way is a good kind of indication of the complexity of things it can handle. There are constructs that Python can't handle. They're almost always the more advanced, newer Python syntax features, just because they haven't been implemented yet in Python. So it's always kind of this Python introduces some new feature in the next version of the language, and Python takes a little bit of time to support that. So it's always kind of a little bit behind, but not too far behind. There are some constructs where it often involves global namespaces and that sort of thing, where the generated code that Python spits out, because we're kind of at the C level, doesn't always work out of the box with the Python global namespace. Python will generate compiler warnings or errors for you in those cases, so it's safe in that sense. And there are some things that it just won't be able to fix based on that, but they're very, very limited. Or if and when you run into them, it's very easy, I've found in practice, to fix them, to correct them in some fashion so that Python and your Python code can work at the same time. I didn't mention it here, but there is a pure Python mode for Python where you can have a valid Python syntax that allows you to declare Python types. So Python decorators with valid, so obviously cdef int I is not valid Python syntax, but you can use this pure Python mode in Python to say, here's this function, inside of this function I'm going to have a C integer I, and Python, when you run it just in the Python interpreter, it ignores it. When you compile it with Python, it uses that information as if you said cdef int I to declare it as a static type. So you can read online about the pure Python mode for Python. It is a nice idea. I find it's not used very often just because people often want the nicer looking syntax of being able to use Python code, but there are definitely projects out there that are using the pure Python mode to have a .py file that can both be Pythonized with good performance and just run without Python at all. Okay. Yes? It uses decorators. It uses just like simple declarations, like you would say I equals Python.int, for example. Oh, good question. Does Python recognize function annotations? So, it does compile Python 3 code. So in that sense, yes, it recognizes them. Does it use them in any way for like adding type information? I remember conversations along those lines, but I can't recall the outcome. I believe since function annotations are now going down a certain road of being used for a certain way of declaring types for type safety, right? There's this whole kind of newer development there. I mean, yeah, that's right, in 3.5. I think because it's kind of settling on that, and because that type declaration is not compatible out of the box with Cython's type declaration, there's, there would need to be some work to make those compatible, and I don't think that work has been done yet. Although it would be very nice to just have that work out of the box so Cython could, use that. It's just that those type declarations aren't meant to be C-type declarations for arguments. So there is some fundamental incompatibility there, right? Like there's so many integer types in C, but in Python we have basically one int type, int and long but in Python 3 it's just one int type, right? So there would be no way to use that kind of newer type declaration in function annotations to specify all the C integer types. So yeah, I'd be curious to know the latest on that though. Other questions? So let's touch on some C++ wrapping in our final minutes here, because it came up a few times. So we have some slides here on profiling. We already touched on that a little bit. So to motivate things a little bit, we have just talking about classes and extension types. A regular Python class is, again, just not surprisingly, just declared with the class keyword. And these are supported by Cython as well. Cython will create a Python class for us if we just use the class keyword and methods and attributes and that sort of thing. And this is just a regular Python class. There's nothing special about it from Cython. It's just that it's implemented in C code, but it still just has all the same semantics. That each instance of a particle has a little dictionary inside of it. It's very dynamic. You can add attributes at runtime, that sort of thing. Now, we mentioned earlier that you can create these new kinds of things called extension types with Cython. And the way you do that is by creating a cdef class. And when you have one of these, now you have something that's a type, a Python type, that's implemented at the C level. And for instance, this particle thing here now is not a regular Python class, it's an extension type. It looks and feels just like a regular object class, I guess you could say, in Python, but it's strictly speaking an extension type. And what that means is it's very different at the C level. Each instance of particle now has a little C struct that it's associated with at the C level. And the C struct has, for instance here, some float arrays, velocity and position, and a mass, m. Okay? And that's what we declare right underneath our particle cdef class line here. These are the instance variables, and you see there's C types that we're declaring. And each little particle object floating around will have this velocity, position arrays, and a mass, m, here. These extension types allow us to have this other kind of initialization called a cinit function. And the job of cinit is to do any and all C-level initialization that we have to do to have a valid object. So for instance, we just take the mass, a position, and a velocity, and we just set self.m to mass, to the m argument, and then we allocate two arrays for velocity and position. This is to, again, give us some room to work with so we have room to put our velocity and our position information. And then we just walk through our P and V arguments and then assign to our velocity and our position arrays here. Okay. So again, we're doing all the C-level allocation and initialization inside of our object here. You can also have an init, just a plain old init here, and it has the same meaning and semantics as a regular Python init. Cinit, though, is specifically for things like allocating on the heap for arrays that need to exist before you interact with this thing from Python. Okay. Yes, you can. You can certainly use shared pointers. I've done that in the past. Unique pointers are a little bit more tricky in Cython. Just it shouldn't be tricky, but it is for some obscure reasons. But yes, shared pointers absolutely work. And I hope to, or at least hope to guide someone to help improve the support for other kind of smart pointers. But yes, this is where you would do that sort of thing. You would allocate, if this were in C++, you can use new, the new keyword, to create objects, and Python will propagate that down, that sort of thing. So we have some regular methods. Here we have a cpdef method on our extension type. So again, if you call this apply impulse on a particle object from within other Python code, it will call a fast version of this, a C-only version of this. But you can also call it from Python, and you'll be using a Python wrapper around this thing. So cpdef, all the ideas and things we talked about cpdef apply to cpdef methods as well. Also, cdef methods work in Python. cpdef methods, though, can be overridden by subclasses. That's one of the big benefits there. You can have a Python subclass of one of these extension types and override cpdef methods. cdef methods, of course, are only available from other Python code. And lastly, we have a dialog method here. And dialog here is meant to undo any C-level things that were done in the C-init. So since we allocated 2 arrays on the heap for velocity and position, we need to make sure we free those arrays when we're done using this object. Python will guarantee that C-init is called exactly once and that dialog is called exactly once when this object is being cleaned up. And it, again, gives us the opportunity to allocate stuff beforehand and then deallocate that same stuff when we're cleaning up this object.
So all this stuff is exception statement, returning exception?
Yes. So yeah, whenever this object is cleaned up in Python, so as you know, Python is reference counted. So when an object's reference count goes to 0, it will be cleaned up. Python will make sure that dialog is called in that instance exactly once. So it's just example showing you the interface, the differences between just regular Python classes and extension types. By default, the attributes on extension types are private. They're not visible. These wouldn't even be visible anyway because they're C-only things. They don't exist in Python. But we can declare attributes public. We can say the M attribute on particle objects can be accessed from Python. And that's what we're just showing here. We can print out mass, that sort of thing. Regular Python classes, instances of regular Python classes are open. You can add new attributes to them, like charge, for example, but extension types are closed. You cannot add new attributes to them, and that's an artifact of the fact that we have a static C struct that's set at compile time. It's not open to adding new attributes there. So we can't add a charge to an extension type particle, for instance. And this really comes into play when we're wrapping C++, because often we're wrapping classes in C++, we want some natural way to expose and represent those classes in Python and in Python. So let's say we have a particle class now that we're wrapping, and we want to kind of wrap that in Python. And we have a very simple interface here, just some public attributes, constructor, destructor, some simple methods, that sort of thing. So the first thing we do to wrap something like this in Python is we, coming to the close here, I'll just be quick, but I just want to at least show this to you. We have our cdef extern from, and then we have our C++ header file now, particle extern.h. And now we use this new keyword in Python, cpp class, telling Python we're declaring a C++ class interface. This here is the name we're going to, the alias for this class internally, so underscore particle. This is optional, you don't have to do this, but, and this is the name to use in the generated code. So this allows us to refer to it as underscore particle internally, but the generated code will only refer to capital P particle here. Okay. You don't have, this isn't just for the CPP classes, you can do this for other things as well, to deal with aliasing and name collisions and that sort of thing. But here we're using it just so that we can call our Python class particle and distinguish that from the class we're wrapping in C++. And we just declare then the interface that we're going to expose to Python. So some attributes, the constructor. We don't have to declare the destructor because Python assumes it's there already. Some methods, that sort of thing. So, and then again, same thing applies as we saw before. Python doesn't automatically wrap this for us. It just lets us use this this class from other Python code. So it's still up to us to create something that will actually be usable from Python and that exposes this particle class to Python. So here we have our cdef class particle. And the only kind of thing we hold inside of instances of particle is a pointer to our C++ particle objects. So we're just going to be using this pointer to get, call methods on it and get data from it, that sort of thing. Instead of seeing it, we just do some simple verification here to make sure the shape and the sizes of our position and velocity arrays are the right shape. If not, we raise a value error. If that passes, then what we do is we call new on our C++ particle class, and we pass in the data so that we can initialize that particle class appropriately. So here, of course, new returns a pointer to a heap allocated C++ object, and we're just assigning that to our this pointer here. So when CNIT is done, we have a valid C++ particle object on the heap that's kind of being referred to by our this pointer inside of our kind of wrapper class here. Okay? Inside of dialog, we simply just say del self.thisPointer. Python will convert, when it generates code for this, it will convert the del into a delete call at C++. So we have a new at CINIT and we have a delete at dialog time. And then we can just declare the methods that we want to expose. So for instance, apply impulse, some arguments, and then we just pass this call through to the underlying C++ object. So we say self.thisPointer.apply impulse. We pass in our data, and we can also declare properties on these extension types. So Python uses a little bit different syntax for properties. It's nice, I like it. So if you want a mask property, you just say property mask colon, and then you define an under get and a under set method, and they just do the appropriate thing. So here we're just getting the mass, and then we're setting the mass. If you declare just a get, or if you raise a non-implemented error from set, then you make it a read-only property. But yeah, this allows us now to be able to say, particle.mass, and it will forward that call to the getMass method on our C++ object. Okay. We have to do a little bit more work to. This is an old way. I didn't use Pythonize here, but one thing you do need to specify is to tell Python you need to use the C++. Make sure you're in C++ mode, basically. And one way to do that is in the extension object that we create here, say language equals C++. You just have to tell Python, oh, okay, I'm working with C++ code now, so you need to switch over and generate code appropriate for C++. So now we put all this together, wrap it up, and now we have this particle class, this particle extension type we can use from Python. We can see p.mass works, for example, just as a regular attribute. We can assign to it. We can call apply impulse, that sort of thing. And if we get rid of the last reference to that object, dialog will be called under the hood for us automatically. Unfortunately, I don't have a kind of example for you here. I'll see about putting together a fully worked example and putting that in the repository as well for those of you who might be interested. Yes?
Is it possible to take those objects that you created in Python and pass them to a C function expecting like a reference to that object?
So you wouldn't be able to directly, like you couldn't pass a plain old particle object to one of those things, but you could pass this pointer.
So you could wrap your function and have it expect that pointer to do so.
Yeah, as long as you just extracted the this pointer and just pass that through, then that will work fine, because the type of this pointer is a pointer to a C++ particle object, which is what it would expect. All right, we're out of time. Sorry I didn't leave more time for questions, but I'm happy to field questions afterwards. If anyone has a couple quick questions, I can field them now. All right, we will, oh, one right here, yes. Good question. Yeah, so I'm horrible about putting doc strings in here, in part just to save some vertical space, but I normally would. But yes, you can absolutely put in doc strings here, and Cython makes sure to make sure those doc strings make their way to Python. You can't, for instance, call cinit from Python or dialect, so the Cython only stuff, it's just internal, but anything that's meant to be used from Python, those doc strings will be sent along. That's right. Yes.
So in all your C++ function signatures, you use pointers. Is there any caveats with references?
So pointers versus references in C++. So no, there's no syntax issues. Cython, you can create reference variables in Cython. It's just that sometimes a generated code, like if you declare a reference variable in C++, you need to make sure you assign to it right away, right? You can't declare it and then assign later. That's invalid C++. So if you have a function that returns a reference, for example, oftentimes you can just use that as if it were a value in Cython, or you can declare things as reference variables in Cython. It's just that sometimes the declaration and the initialization are broken up in the generated code, and so you might get errors as a result. So oftentimes it's best just to cast to a pointer and use that, because Cython, it still just uses .NET syntax for pointer variables, or just use a value type and have it just dereference for you and get the value out. All right, we will adjourn. Thank you, everyone.